Oh, good afternoon, everybody. I think I'll make a start with this. Welcome to, 22nd NANOG. This tutorial is BGP for Internet Service Providers, where I've been given the relatively impossible task of trying to do a BGP tutorial in 3 hours. This one is going to really start at the beginning with a very, very quick recap over what BGP is and so forth. I'm going to try and aim it towards people who have used BGP before but only really dabbled with BGP, rather than trying to aim it at the Tier 1 service providers who probably know it far better than I do in any case. Right, my name is Philip Smith. I work for Cisco Systems. I've been working for Cisco for about 3.5 years. I'm based in Asia Pacific region. I live in Australia. All my work is spent with working with service providers in the Asia Pacific region. So I've worked with most of the big ISPs in Asia Pac. Before I joined Cisco, I worked for UUNet. I ran UUNet's UK network, probably for a couple of years after UUNet took over. Our small UK ISP startup. Some of you may have heard of Pipex, which was started in 1992. I was one of the first people who joined there. So that's my background. Let's have a look at what we're going to be doing. Is everybody okay with me standing here? I prefer to sort of stand, wander around, point at the screen, rather than be perched up on the platform. Is everybody okay with that? Yep. Okay, so what we're going to be doing this afternoon is really having a look at these six points. As I said at the start, we're going to have a quick recap over some of the BGP basics. I'm going to try not to get too complex with it, but again, not make it too quick so that those of you who haven't really seen much of BGP before will see where we're at. After the basics, we'll have a look at scaling BGP and then deploying BGP in a service provider network. That should take us approximately to the break at 3 o'clock. It just depends how quickly I talk, how many questions people ask, and just how we get on. After the break, we'll have a look at potential trouble spots, how to avoid trouble, and some troubleshooting examples. Again, I think that part of the presentation could be a whole day in itself. So I've tried to pick some of the more common things that I find in my day-to-day life and show them to you here. The second final point, multi-homing examples. These are only 1 or 2 examples of multi-homing. Again, I think multi-homing could easily be a day-long tutorial. I mean, there's just many, many ways of dealing with that particular difficult subject. So I've tried to give 1 or 2 examples, give you some food for thought, rather than just trying to take up the whole of the day on that particular subject. And then finally, I've documented some uses of communities as a use for BGP, as a use for multi-homing, in the final few slides of the presentation. Okay, so that's the gist of what we're going to do this afternoon. So I'd say the first hour or so will be more simple, the remainder will be a little bit more complex. Okay, so what's this BGP thing? Well, BGP stands for Border Gateway Protocol. A routing protocol which is used to exchange routing information between networks. Documented in RFC 1771, which is pretty old RFC these days. The current Internet draft, which describes the latest state of the standard, is that one, draft ITF IDR BGP4 12.txt, which you can get on the ITF webpage if you're interested. Okay, so that pretty much documents the current state of BGP today. An autonomous system. All of you will have heard what an autonomous system is. You hear people talking about AS numbers and so on. An AS is basically a collection of networks with the same routing policy. Okay, so the picture there has a few routers, some lines drawn between them, and a number. And that is basically an autonomous system. You run a single routing protocol with an autonomous system. An AS is usually under single ownership, trust, and administrative control. I say usually, in about 90% of the cases. BGP basics. Well, it runs over TCP, uses port 179. This is something that several people I've noticed make a mistake. They do very, very good filtering on the edge of the network, and they completely forget to allow BGP through. And we have a frequently asked question of, my BGP won't come up because it's been filtered. So TCP port 179 is used by BGP. It's a path vector protocol. It relies on incremental updates. Okay, so only changes between routing information or between state are announced by BGP. BGP will never send the entire routing table in one big hit. You have a concept of internal BGP and external BGP. Two autonomous systems talking to each other usually have two routers on the edge, border routers A and C in that example, and these two routers will peer with each other. Peering is basically exchanging routing information. The bit of network in between two autonomous systems is called the demarcation zone, or demilitarized zone, whatever, right? DMZ. That is the shared network between the two autonomous systems. It's not owned by anybody, or it's usually under common ownership, depends on the situation. So I've got two examples here. Between A and C, we've got a point-to-point link. So that could be a leased line. So this could be a leased line here. Or we've got this one, which could be a shared Ethernet, for example, at an exchange point. These are very much a demarcation zone. Now, BGP's general operation. It learns multiple paths via internal and external speakers, picks the best path, and installs that in the forwarding table. The best path is sent to external BGP neighbors, and the way you apply policies is by influencing the best path selection. That's basically how it works. Now, external BGP, often people just represented it as eBGP, lowercase or uppercase e, depending who you are, where you are. eBGP is BGP talking between different autonomous systems. Right? We've got AS100, AS101. Router A will talk eBGP to router C. Okay? The network in between needs to be a direct connection between router A and router C. In 99% of the cases, you have a direct physical link between A and C. One thing to note, for good practices, never run an IGP between eBGP peers. Again, I've found in a lot of cases, service providers starting up networks, they will run an IGP between routers A and router C, because that's the way you get reachability information between the peers. You can do that, but the amount of accidents you can get in this particular situation, well, you just don't talk about it. Okay, so it's never done. Configuring it, well, I've put up Cisco iOS configuration here. If you've never seen iOS configuration before, I hope it's intuitive enough for your own router that you use. But again, the configuration should be fairly straightforward. There's a perception, certainly in service providers starting off, that BGP is really, really tough to configure. And I think my main motivation for putting this up is saying it's not really that difficult. Okay, it's not really that difficult. You specify your interface, you've got the address on it, configure your BGP with autonomous system number. I'm sorry about the colors, they look a lot better on my screen than they do here, but this is 100. You configure your neighbor, pointing to your remote autonomous system. You've got some filters. This remote autonomous system will point to the BGP on the remote router. Okay, so that's quite straightforward. You've got the correspondence, AS100 here, points to AS100 there, 101 here, points to 101 there. Okay, so that's configuring external BGP. Internal BGP, well, it's represented as iBGP. Here, the BGP peer is within the same autonomous system. This time, we're not required to be directly connected. The iBGP speaking routers don't need to have a direct physical connection to all their neighbors. Right? That's completely different from eBGP. However, the iBGP speakers do need to be fully meshed. Okay? They need to be fully meshed. The reason for this is that iBGP speakers will only originate networks which are connected to them or pass on prefixes which they've learned from external speakers. Okay? IBGP speakers will not pass on prefixes that they've learned from other IBGP speakers. The whole point of doing this way back when BGP was first developed was so you wouldn't end up with routing loops and duplicate information. Okay? But this is why we've ended up with this situation. IBGP speakers need to be fully meshed. It looks something like this. We've got, well, three routers, A, D, and E. The purple lines here represent the IBGP conversation. It's independent of the topology. Router A is talking to router E, but there's no physical link between them. Likewise, A is speaking to D, no physical connection between them. And as I said before, every speaker needs to be fully meshed. Right. Another good practice with IBGP is to set up the peering with a loopback address, or with some interface on the router that is always there, which is never ever going to go away. Okay? Right. So in this example, I've set up loopback interfaces on all my routers, and I set up the IBGP session to run between the loopback interfaces. You don't want the IBGP session to be dependent on the state of a single interface. And if you look in your backbone today, if you look in any ISP network, most of the ISP backbone routers have at least two interfaces connecting elsewhere on the network. So if one interface goes down or one circuit goes down, you'll have an alternative path via the other interface or interfaces. Right? Take advantage of this. If you configure BGP to run between loopbacks, then even though you have infrastructure problems, your IBGP remains functioning. And that gives you the stability that you require. Configuring internal BGP, well, again, a configuration snippet. You set up your loopback interface with a /32 mask. Router BGP 100, remote AS, notice it's the same one because it's internal BGP. Updates come from the loopback interface, and here's router B. Again, same AS, AS100, this one pointing back to router A. Notice the IP address here is the loopback interface address of router A. Okay, BGP attributes. Again, just a quick recap. The AS path, first attribute we'll look at, it's a sequence of autonomous systems a route has traversed. Okay, so if AS100 is originating network 180.10/16, he will pass it to AS200, 200 will pass it on to 300, 300 passes it to 500. So we look on a router, an AS500, we see the prefix 180.10/16 with a string of numbers listed with it. That string of numbers is the AS path, the list of autonomous systems the prefix has basically passed through. Right, so 300, 200, 100. Well, I've heard it from 300, 300's heard from 200, 200's heard it from 100. The AS on the extreme right is the AS which has originated the network announcement. Okay, so you want to find the origin AS, it is this one here in the extreme right. And the AS on the left here is the one that you've heard it from. So AS path is fairly simple to understand. What's it there for? It's part of the whole loop detection process for BGP. Okay? If, for example, AS500 had a link that connected it back to AS100, well, 500 would hear this prefix coming from 100, and it would try and pass it back to 100. And 100 would then hear this prefix from itself, as well as seeing it from 500, and you could potentially, if you had no loop detection, end up with a prefix announcement going round and round in circles. Okay? So, any AS which announces a prefix, so if say 500 announces a prefix back to 100, it sees this AS100 in the AS path, so it won't actually make the announcement back to 100. It will drop the prefix before it's announced. Likewise, AS100, if it hears any prefixes coming from another autonomous system with its own AS in the AS path, it will drop that announcement. It won't even process it. It will drop it before it's even received. Okay? The other thing the AS path is used for is applying policy. Okay? It's actually very, very powerful for applying policy from BGP. Policy is basically how you communicate between you and your neighboring ASs, what you accept and what you receive. So AS path is very useful for that. The next hop. Well, the next hop is basically the neighbor address you need to get somewhere. So for example, AS200 originates this network, 150.10/16. He will pass it on to AS300. So you look in router B, I hear 150.10/16 from 150.10.11, which is the IP address of this point-to-point link. So that is the next hop. Right? For eBGP, the next hop address is actually the address of the external neighbor. For iBGP, well, the next hop is what's heard from eBGP. So if you look on router C, the next hop is still this address here. The next hop is not changed as it's passed within a network by iBGP. Even though you look at this and think, yeah, this is all obvious, this is the biggest problem I find in service provider networks today. People forget this really important thing. The external next hop is carried across the backbone by iBGP. I do a lot of ISP workshops, both for Cisco and for other organizations independently, and it's guaranteed that 30 to 50% of the class, when they're trying to configure this, will completely forget that this point-to-point connection needs to be visible across the backbone. Okay, it's a very, very common mistake. iBGP next hop. Another thing to note with next hop in the iBGP network, for example, you have a network connecting to router B, for example, a customer. He's got, say, 220.11/24 network. Router B is originating this prefix into the backbone, into the iBGP mesh. The loopback of this router is, well, say, 221.2542 as the address. If you look on router D, which is also part of the full mesh, 220.11/24 has a next hop of the loopback interface. Because remember, you were using loopbacks to talk iBGP across the backbone. Right? iBGP runs between the loopback interfaces within this network. So any prefixes you see within the backbone, for example, on router D, you see the next hop pointing to the loopback. So again, yeah, feel free, ask questions.
Why would you not use loopbacks on the
How do you, okay.
Why would you not?
Okay. Right. The question is, why would you not use loopbacks on external BGP? The answer is you can. I was going to come to that quite a bit later. But in the default case, you don't, because then the question is, how do you get to the external loopback from where you are within your network? You need to set up some, entry in the routing table to point you to the external loopback. Okay? There's a way of doing that, basically. But for external loopback, the default case I would say is use the point-to-point connection, and for internal, inside the network, use the loopback for the point-to-point connection. Okay? So generally, if you look inside the iBGP, any service provider network, you find all the customer prefixes listed here, and then the loopbacks of the routers inside the backbone listed as the next hop. This leads to an important point. You need to carry the loopback interface address around the backbone. Okay, it's really, really important that the loopback interface address is carried around the backbone so that all the routers can actually see each other and that the next hops are reachable. Third-party next hop. This isn't really something that you can configure, it just is a thing that happens. Take this example. If you have eBGP between router A and router C, and you've got eBGP between router A and router B in these three ASs, well, router A passing the prefix to router C, say the 192.168.1 network, router C will use this address as the next hop because it sees that this network is in the same LAN as it is sitting on. Okay? So rather than traffic going from AS200 to 202, rather than going from 201 into 202, it will go direct over there. Right? So that's a third-party next hop. It's designed to be more efficient. You don't have traffic doing a double jump through router A. Of course, it's got downsides as well. Router A and router B or P have a peering relationship with each other, but A and C have, well, or AS201 and 200 have no wish to have any relationship, 200 has no wish to have a relationship with 202. You can end up having traffic going from 200 to 202 with 201 just sitting in the middle doing the necessary. Okay, so you've got to watch the third-party next hop. You can also get third-party next hop if you have an iBGP session. Say this is one autonomous system, you can have a third-party next hop here. Router A is the only one that has a peering with router C. Router B doesn't have a peering with router C, well, for whatever reason, but it has an iBGP session between A and B. That way it can be a little bit more efficient as well. Right? C will send traffic directly to B for prefixes that originated here. So there the third-party next hop could be a bit more useful. And certainly in my day, we used that quite a bit for the way that we connected to UUNet AS701 in the United States. Yes? This is default behavior. It doesn't have to be configured at all. A lot of people don't know about it, and they get a little bit afraid when I say, well, yeah, this just happened. You've got to be really, really careful when you're doing external BGP peerings across a shared media like that. Really, really careful. And I've got a few more slides in the second half that cover some more examples. Okay, so the summary for the next hops. This is really the first time I've mentioned the IGP, the Interior Gateway Protocol. Okay, the IGP should be used to carry the route to the next hops. You want to put all your next hop information in IGP, OSPF or ISIs. Okay, so the point-to-point link, external point-to-point links go into your IGP, and your loopback interfaces. All those addresses go into the IGP. You want to rely on recursive route lookup. BGP will look for its next hop in the IGP somewhere, somehow. The good thing about this is it unlinks BGP from the actual physical topology. The United States is very, very lucky because we've got very reliable infrastructure here. If you work in some of the countries I deal with, trying to maintain a stable BGP within the backbone is hard work. So service providers pay a lot of attention to making sure that BGP is really well unlinked from the physical topology. Yes?
We're going to talk about the most typical ways most ISPs inject the next hop address into the IGP with redistributed connected or next hop self, or are you going to touch on that?
Okay, the question was, am I going to talk about how ISPs, put prefixes into BGP, how they're using the next hop, redistribute connected, and so forth? The answer is yes, I will do a bit later. Okay. Right, so as I was saying, the main reason is you want to try and unlink BGP from the physical topology. You want your IGP in the backbone to remain really, really stable. This is very important. And it lets the IGP make the intelligent forwarding decision. IGP is generally much better suited to figuring out the best path to get places, doing a fast reroute if any infrastructure breaks, and so on. Origin, this isn't used anymore. Well, I don't think it really should be used anymore. Conveys the origin of the prefix. As far as I can see, it's a completely historical attribute. It's used as part of the BGP best path selection process, where BGP works out the best path. The three values: IGP, where it's been generated from BGP itself; EGP, where it's been generated by the old EGP routing protocol from years and years ago. Incomplete means that the prefix has come from some other routing protocol. Okay? I really don't see many who are making much use of this today. Most service providers are setting the origin to IGP, and we're just leaving it. The main reason for the origin was the transition from EGP to BGP many years ago. So it shouldn't be used. Aggregator conveys the IP address of the router or BGP speaker which is generating aggregate route. It's not really used for anything apart from debugging. You find out who has generated aggregate. So it tells you the IP address, the router ID of the one that's been generating the aggregate. Okay, local preference. Local preference is probably one of the more important attributes. It is used for determining traffic flow out of a network. For example, AS100, 160.10/16, it's being originated by there. It's announced to AS300, to 200, and it reaches AS400 and router C in particular. And we look in router C, we see two paths. We can go this way to get back to 100, or we can go that way to get back to 100. And most ISPs don't really like a random path out of the network. They want things to be determined. They want to determine which way traffic's going to go. Should it go the left way? Should it go the right-hand way? Okay? The way you do this is use local preference. So for example, AS300 will announce his prefix to router B. Router D in AS200 will announce the prefix to router A. AS400 is setting local preference on the announcement. So he's setting local preference 500 and what comes in from router D, and he's setting 800 and what comes in from router E. Highest local preference wins. Okay, it's really important to remember that. Highest local preference wins. So we're setting at 800 here and 500 there. He's saying he wants traffic to go out of his network to 160.10/16 via this path. Okay? So local preference determines how traffic will flow out of your network. Local preference is local to an AS. It's a non-transitive attribute. Default is 100. Used to influence the BGP path selection. As I said, outbound traffic. And the path with the highest local preference wins. Configuration, well again, this is just an example of how you might set local preference. Use something called a route map, where you basically match the address or the prefix you want to match against, 160.10/16. If you match this, you then set local preference to 800. Okay? Question? Okay, question is, you've got two links and they've got the same local preference. Do you load share? No, you're part of the BGP path selection, which I'm going to cover in a little bit. So it moves on to the next selection criteria. Okay. MED, multi-exit discriminator. Well, those of us in the old days call it metric. All mean the same thing. This one is the opposite of local preference. Right? MED is used to determine how traffic will flow into your network. So if you've got a network here, 192.6.8.1/24, you're announcing it to AS200. There are two paths between you and AS200. You want to tell AS200 which way traffic should be coming into your network. And the way to do that is set the MED, or MED. So router A, well, we set a metric 2000, an announcement to router C. B, we set a metric of 1000 on an announcement to router C. In this case, lowest metric wins. And again, I find the people who are learning BGP have great trouble trying to remember, okay, local preference is high, metric is low, and it's like, well, why, and so on. Once you start configuring these, playing with them, you remember very, very quickly which one wins. But in this case, it's lowest metric wins. Okay, so the path with metric 1000, coming from AS200 into AS201, C to B will be the path that's preferred. Okay, again, MED, is that a question?
I was going to ask if you could cover the
Yes, I will cover all this.
I have heard that some ISPs don't accept net from other ISPs.
Okay, yeah, question or comment, some ISPs don't accept meds from customers or other ISPs. Yes, that's quite common. It's quite common. It's getting more common these days. Okay, but I guess so. Could be one of the reasons. People using local preference, and they're going to use communities, which I'll cover a little bit. And in fact, there's some people go as far as recommending not to use MEDs anymore. Okay, but some people still use them. It just depends what you and what your upstream agree to do. I think think as we go on, you'll see some of the reasons why MEDs are getting a little bit less in favor because of various issues around them. But anyway, we'll just cover this for the time being. MEDs used to convey the relative preference of entry points, so best path for inbound traffic. It's only comparable if paths are from the same AS. Okay, so if your paths are from different ASs, by default, MEDs are not compared. And you can convey the IGP metric as an MED if you want to. So if you have a low bandwidth path to your border router and a high bandwidth path to another border router, you can convey the relative metrics, IGP metrics of these paths via the BGP MED if you want to. Configuring it, well, again, it's not really that hard. Again, you use a route map which matches the particular address you want to set the MED on. Then you just do set metric 1000, like that. So it's, again, it's quite straightforward setting the metric. I've put weight in here. Weight isn't an attribute, but it's so akin to how local preference works that I think it's worthwhile mentioning it. And for a long time, weight, well, some people called it a Cisco-specific attribute, which I'll say it probably is. But it's actually really, really useful. It's a local preference which is local to the router only. And the main use of it today is to help deploy the reverse path forwarding checks. Okay? For example, we've got AS4 here and AS1 there. We've got a big link which is going to be used for most of the traffic, and this little link here which is basically the backup between the two ISPs. Now the way we make this the preferred link between AS1 and AS4 is to set a high local preference on the announcements. Okay, so set local preference 200 here. We've got the default local preference 100 in there. So all the traffic from AS1 to AS4 will go over the big link that way. Okay. Now, if you want to do a reverse path forwarding check, where basically we verify or we check the source address in the announcement, whether it's actually heard that way. So anything coming in with, say, any packets coming in from AS4 onto this router, you check the source address. If it came from AS4, well, without setting any weight, you'd see the best path is actually around this way. So you'd see an asymmetric path and the packet would actually be dropped. But if you set a weight, you're basically telling the router that this is a more important path. So any announcement coming in from AS4 to this router, you set a high weight on this. Now, with a local preference, it only applies to the local router. This would tell this router that this was the best path to get to AS4, and the reverse path forwarding check would actually succeed. Okay? So you find today that the most common situation for deploying RPF is, most common situation for using weight is for people deploying the RPF check. If we look back through the years and common service provider networks, ISPs would use weight to give sort of local priority to exit points of the backbone. We had some customers who connected to our border router. They paid us lots of money to do that, and we would use weight to actually give them the best path out of a backbone, rather than carrying their traffic across different parts of a backbone. Okay? I think the best way to think of it is a localized local preference. Okay, community. Community is a really important attribute. In fact, well, certainly within my team in the UK, we consider this one our lifesaver. I mean, this really did save our lives big time. I think it was about 1995 when it was first appeared in BGP. BGP attribute is described in RFC 1997. It's a 32-bit integer, but it's represented in internet use as two 16-bit integers. And the main point of the community is it's used to group destinations. Right? Destinations can be members of one community or multiple communities. It's extremely useful for applying policies within ISP networks or between ISP networks. Right? And as we go through the presentation, I'm going to show you some examples of communities. And that right at the end, I'll show you some examples of communities that are in daily use in service provider networks. Okay? The community attribute is carried across ASs. It's a transitive community. You can basically send it as far as you want. Here's a simple example. We've got this ISP here, ISP1. He's an AS300. He's got some customers, an AS100 and 200. These customers are announcing prefixes into his network, and he's tagging these prefixes with community 300:1. That's a representation. Internet convention is that the first number here is your autonomous system number. The second number there is something between 1 and 65535 that you can do with as you wish. Okay, that's the general convention that's used today. It was used in RFC 1998, which I'll cover later on, and I think most service providers have stuck with this. It's actually quite easy. You can look at this number and it makes sense, it's understandable, compared with trying to deal with a 32-bit integer, which is big and meaningless. Okay, so router C will tag what he hears from these two autonomous systems with this community 300:1. He's peering with ISP2, community 300:9 is what's attached to this network coming from ISP2. Router E is connecting to, well, AS400, and the deal with them is he's only going to announce his customer prefixes to AS400. He's not going to announce his peers. So, and the way he's going to do it is use communities, right? Community 300:1 is what's set up in the filter on router E. Right? So router E talking to AS400, I'm only going to send the prefixes in community 300:1. I'm not going to send any other prefixes. Of course, people tend to say, well, you could just use prefix filters or AS filters, couldn't you? And the answer is, well, yes. What happens if AS100 then starts adding or announcing more prefixes to you? Okay? You've then got to change your filter here and change your filter there and change your filter in half a dozen places throughout your network. Whereas if you're just tagging with a community 300:1, your filter is immediately updated there. You don't have any work to do because you're allowing everything within this community into AS400. Right, so you're just matching. Is it in community 300:1? Yes, we send it here. If not, it doesn't get to go. Right. And this is what I meant earlier by saying it was a lifesaver for us, because in typical ISP fashion, salespeople sold all sorts of services which engineering had to make work a few hours before the customer was due to go live. And so external filters tended to be a complete mess. Right? When communities came, we could vastly simplify it by putting all the different customers into the different communities. And then we just announced the appropriate communities at the correct edge points. It made life so much easier. There's some well-known communities, well, 3 of them. There's no export, which basically says do not advertise to any eBGP peers. There is a no advertise community, which says don't advertise to any peer. And there's a local AS community, which says do not advertise outside the local AS. And this one I've generally seen used only with confederations. If you don't know what confederation is, it'll be covered later on. The no export community is actually used a lot, a great deal. Mostly in this type of situation. You've got one network here, he's got multiple links to his upstream. He's trying to do load sharing on these links. And the way he's doing his load sharing is he's taking his address space, say out of 170.10/16, and chopping it into lots of little pieces. Okay? So what he does, he announces all the little pieces to his upstream. Well, you don't want to announce all these little pieces to the internet. Right? That's definitely a very bad thing to do. So what you do is you tag the little pieces with the no export community. You still announce your aggregate to the upstream. Okay? You still announce your aggregate, but all the sub-prefixes you tag with a no export community. And router G will strip out all the prefixes tagged with no export automatically. Okay? So where G connects to external networks, all the no export communities will be automatically stripped out. Okay? So that's actually very useful for load sharing. Right. The BGP path selection algorithm, or why is this the best path? What I'm going to show here is slightly different from what's documented in RFC, but just to give you a rough idea of what's actually happening in the path selection algorithm. The first one is, do not consider path if there's no route to the next hop. Well, this one is actually very obvious, but a lot of people forget about it. This is why it's really, really important to have the next hop in your routing table. Notice in routing table. A common mistake is people look in the BGP table and say, oh yeah, next hop's there, that's fine. BGP table is not enough. It's got to be in the routing table. Okay. Second one is peculiar to Cisco iOS. Don't consider the BGP path if it's not synchronized. Synchronization we'll cover a bit later. The next one, take the one path with the highest weight. The weights are all the same. We then take the path with the highest local preference. So local preference, as you see, is really, really powerful. It's probably the first attribute that's of real use to you. Okay, local preference. You can override everything else with local preference. If local preferences are all equal, then we prefer locally originated route. So if the route's been originated by the local router, then you prefer that one over being originated by anywhere else. We then take the shortest AS path. I mean, again, it's a typical internet thing. You always want to take the shortest path to get somewhere. Why go over a path with 5 AS hops when you can work with one that's just 2 or 3 AS hops? Okay? So you pick the shortest AS path. Notice highest local preference comes before AS path length. And if somebody sends you a long AS path, you can override that with local preference if you want to. Next page, lowest origin code. Well, origin code shouldn't matter anymore these days, so we can skip this one. Lowest multi-exit discriminator. Well, the RFC says MED is only considered if paths are from the same AS, and that's the default behavior. But we can change this. You can compare the MED from different ASs if you want, and the way to do it is have this particular knob always compare MED. In this case, you always compare the metric no matter what the AS path is. Okay, so if you hear the prefix from different ASs, you can switch this on and then compare the MED. This one I will cover a little bit later. Deterministic MED, where the paths are ordered before comparing. And that's actually really important because it makes the route selection process a lot more stable than the default action did. Okay, but I'll cover deterministic MED a bit later on. Next page, final page. Prefer eBGP path over iBGP path. That says take the external path rather than the internal one. That's the BGP nearest exit thing. Again, you look at most service provider backbones. Most backbones will try and dump traffic that goes outside the network as quickly as they can, okay, rather than carrying it across the backbone. So that's the default behavior of BGP. Path with the lowest IGP metric to the next hop. In other words, take the highest bandwidth link to the next hop. If this is all the same so far, we then really get into what I call danger zone. I never really like seeing the path selection going down here, because a lot of this, well, it can get out of your control at times, but it starts depending on features of your network, which may not be too good. It gets down to, well, lowest router ID. What IP address has been used for the router ID in the router? Shortest cluster list. This applies to route reflector, which I'll cover a little bit later. But that's if the client is aware of route reflector attributes, and if it's not, well, we then skip on to this, lowest neighbor IP address. And of course, neighbor IP addresses could change. You add more routers to your network, things can be different. You really don't want to get down here in the path selection algorithm. But BGP has to pick a best path always. It can only forward the best path, it can only put the best path in the forwarding table. It can't put multiple entries. It's got to make a decision. Right, so it wanders all the way down to here. And because each IP address is unique, well, this is pretty much a final decision for the best path algorithm. Now, applying policy with BGP and giving yourself some control. Well, for applying policy, decisions can be based on AS path, that one's very common, community that's being set, or the prefix. These are the three things that people use today for deciding how to apply policy on the network. Now, applying policy is all about rejecting or accepting selected routes. And the way to do it really is set attributes to try and influence the best path selection algorithm. Right? You can change some of the attributes that have been set. Local preferences, MEDs, AS paths, communities, etc. The tools that you have available, well again, on iOS, these are prefix list for filtering prefixes, filter list for dealing with ASs, AS paths, route maps, and of course, communities. Communities are really, really powerful. So, prefix list. Well, here we're filtering routes based on prefix. It can be applied inbound and outbound, of course. We set up a peering with our neighboring AS, AS210, and then we filter inbound and we filter outbound. Inbound filtering, we basically say we deny network 218.10/16, we accept everything else. So inbound, we're blocking one particular prefix, accepting everything else. Outbound, well, we're only going to allow 2157/16 out. That might be our aggregate block, for example, and we're blocking everything else. That's a simple example of doing filtering based on prefix. You can do filtering based on AS path. Again, similar peering, AS210, filter list 5 out. So list 5 points to this IP AS path access list thing, which basically says permit and hat $200. Because those of you who have seen this before will know this means prefix is coming from AS200. The hat basically means start of a line. It's a regular expression. 200 is the AS number, dollar is the end of the line. So if the AS is exactly AS200, or the AS path attribute is exactly AS200, then this prefix will be announced out in the peering. Filter list 6 in, permit and if everything that's come from AS150 only. Okay? So that's, again, a simple example. A couple of slides on regular expressions. They're a bit like Unix regular expressions, but not exactly the same. There are subtle differences. So I've listed some here. Dot matches one character. Asterisk will match any number of preceding expressions. Plus will match at least one of the preceding expression. Hat is the beginning of a line. Dollar is end of a line. Underscore is beginning, end, white space, bracket. Vertical bar means or. Brackets are used to contain expressions, and there are a whole lot more. And some simple examples. Dot star means match anything. Dot plus means match at least one character. Hat dollar means match routes local to this AS. Okay. Underscore $1800 means anything which has been originated by AS 1800. Hat 1800 underscore anything which has been received from AS 1800. Anything which has passed through AS 1800. You don't care what comes before or after, but 1800 must appear in the AS path. This one, anything which has passed through both 1800 and 790. This one, match at least one of 1800 in sequence. So if AS 1800 has been using AS path prepend, in other words, putting more 1800s in the AS path, this will match it. It will match multiple occurrences of 1800. And another, well, surprisingly frequently asked question for those who are using confederations, how do you do regular expressions for confederation? Because the ASs appear slightly different there. And this is how to do the confederation AS match. You put a backslash brackets for this confederation AS number. Okay, a route map. It's a bit like a program for iOS. That's probably the easiest way to think of it. It's got line numbers, a bit like programs. Each line has a separate condition and action. And this basically works on an if-then-else type construct. Okay, if match, then we do the expression and exit, otherwise we move on, etc., etc. Just so you understand the next few examples. So doing a bit of policy control, slightly more complicated route map. We do an in filter in. This route map will then match this particular IP address. So matching network 10/8. If we hear 10/8, we set local preference 120. If it doesn't match, we then jump on to the next line. Does the prefix match this one, 20/8? If it does, we set local preference to 80. If it doesn't, we jump on to the final line. Okay, so that's just an example of how you would set local preference in a sort of cascading function with route maps. For filters, filter list, similar type of thing. We can match on the AS path here. So anything that's been originated by AS150, we set local preference to 80. Anything which has come via AS210, in this one we set local preference 200, and so forth. Okay, so that's using a route map to filter on AS path. We're setting local preference depending what we've heard on AS in the AS path. Example configuration of an AS path prepend. For example, if you're connecting to neighboring ISP, you want to make the AS path appear longer than it really is, usually for reasons of multi-homing, which we'll have a look at later. You do it like this. You've got router BGP statement, remote AS100, route map, set path. Okay? And the set path route map basically doesn't do any matching. It matches everything that is heard. And we then do set AS path prepend 300, 300. So there I've added 2 more AS300s to the AS path attribute. Okay? So the neighboring router in AS100 will see 3 instances of AS300 in the AS path. Okay? It's really important to use your own AS number. Okay? I wish there was something that you could actually do that wouldn't let you type anything else in there. You can put another AS number in there if you want to, but expect to have problems. Okay? Right? If you put somebody else's AS number in there, expect that the BGP loop detection will cause disconnects. I mean, I've seen people put different AS numbers in there for other reasons. So sort of really, really advanced traffic engineering. But this is like, definitely don't try this at home, right? Unless you know what you're doing. Yeah, question?
Why would you do the prepend?
Why would you do the prepend?
Yeah.
It's to help you multi-home. I suppose the example might be you've got, I'm jumping way ahead of myself, but the example might be you've got links to different upstreams. One link may be low bandwidth, other one link could be high bandwidth, or one upstream may have a very tortuous link to the internet core, whatever that is. So you may want to make his path look longer than it really is. Yeah.
I can add that. The multi-access distributors use the same role, but it's not a representative. If there's after attachment comparison, then if you've got different AS paths, then other devices taking shorter AS paths, not paying attention to your MED. So even if you're ever using that on the internet, it's going to be equivalent. So you can use the continue to use that graph from you by making a particular path look like a lot longer.
Okay. Now, I have got an example much later on in the multi-homing section with a picture which shows exactly this. So you'll see that now. Okay. Okay, setting communities. So an example of how to set community. This is the example I showed you a few slides ago about the no export community. Again, BGP configuration, remote AS200. iOS by default does not send community to external neighbors, so we need to set this. So to the external neighbor, send community. Then a route map to set the community is here. So we want to match all the prefixes that we don't want our upstream to announce to anybody else. So to do this, we have prefix list no announce. Prefix list no announce is basically all the sub-prefixes of the /16 network. Okay? So anything, all the sub-prefixes of 172.168/16, we set community no export on. Okay? Everything else we leave alone. That's an example of how to set the community. If we want to match communities, well, again, we set up a route map to do this, filter on community. On the route map itself, we match community 1. This points to a community list here. So if the prefix matches either of these communities, we set the local preference to 50 in this example. If it doesn't match community 1, we then jump on to the next line. If the prefix only belongs to community 88:6, we then set local preference to 200. Right? That's what the exact match thing means. So you've got a fair amount of flexibility in here to pick and choose what to do based on community. Okay, question?
Yeah, sorry. I've got a couple of things on that slide. Can you clarify, 6 slides back, which parts in the set community are referring to like symbolic network iOS specific, and which part is the instruction space?
Okay. Okay. The mic's not going to come that far. Right. Okay, the no export is the well-known community. Right. So this is basically a name that I've made up. Okay, and it points to this prefix list down here. This prefix list basically says out of this /16 network, all prefixes which are /17 and longer. So 17, 18, 19, 20 to 1, all the way to 32. So all these sub-prefixes will fit in there. So it's not the 16 itself, it's all the smaller ones. All right? If the prefix coming in matches this prefix list, we then set the community to no export. No export is the well-known community. Okay? Everything else we leave alone. Right, this name set community, okay, it's probably a bad choice of names. That's just a name that I've made up. Right, this is just a name. Jumble of characters that I've used to call this route map. Does that answer? No exports are well-known community. It's called this, well, in iOS it's called this. It has a number, which I don't remember off the top of my head. It's in the RFC. Yes, was it 65535:655, something like that. It's in the RFC. I don't remember it.
So a recommendation you probably know is you should design meaningful tags to communities you're going to manipulate and use the meaningful tags, not the numeric values in iOS.
Well, this is, I think in iOS they've just given those 3 names. I mean, you can't assign meaningful tags to the rest of them. Right, the rest of them all appear as numbers, AS : a number. But you would keep within your own operational database, you keep a list of communities and what they actually mean. You can't put those in the configuration. Okay? It's just that these 3, no export, no advertise, and local AS, are keywords within the iOS configuration. That's all that is. Okay? So,
Next few slides are about BGP capabilities. Not necessarily some of the extensions that have been added on to BGP or some of the ways, well, one of the ways of extending BGP. BGP capabilities are documented in RFC 2842. Basically, capabilities parameters are passed around in the BGP open methods. So the router wants to bring up a session with the neighbor, it will say, I support capabilities and I can do this, this, and this. And the neighbor can either say, go away or whatever. Unknown unsupported capabilities rolls out in the notification message. It's quite interesting when capabilities first appeared that some of the implementations didn't actually cope with these very, very well. To get something unknown in BGP, you're meant to just ignore it all over. Anyway, capabilities are around now. The main uses are multi-protocol extensions to BGP. That's been really the major motivation for it. So, for example, for IPv6 version BGP or MPLS version BGP, carrying multicast, prefixes BGP, all multi-protocol extensions have the capability code 1, that's RFC 2858. That refresh was covered a little bit. For the capability, cooperative multi-porting capability, that's mentioned at graph somewhere at the moment. And multiple routers to destination capability, well, that's just pure density from RFC editor, haven't been following that one. And basically, that's pretty graphic. Basically, it's an open session, you see the capability code mentioned there, what it can and what it can't. This is a BGP session, you brought up the unicast as well as multicast.
scaling BGP. So, question, how do you scale IBGP mesh beyond the few peers? Those of you who are new to this would have probably thought, okay, this sounds reasonable for 10, 15, 20 routers. What happens with 1,000 router network? How do you do your full IBGP mesh there? Also, how does this make policy about policy flags and route sharing? Very important today. How do you keep overhead on routers? Probably not so important today. Not as important as it was 5, 6 years ago when the Motorola process was due. And also, find out how to keep the network stable, scalable, and simple. And these 4 things we want to look at: dynamic reconfiguration, view groups, write-back damping, write-back configuration. Okay, first one, dynamic reconfiguration, or basically soft reconfiguration like refresh. But if you do a hard BGP clear after you make a policy change, which you need to do, you basically have to bring the BGP session down, bring it back up again, because you haven't stored prefixes you've heard from your neighbor that were thrown away due to the policy. So that's a basic problem. You do a hard clear BGP, say you have a routing table, that's a big table on the CPU. Also, you do a hard clear, you no longer manage the prefixes, aggregate blocks, you disappear from the internet. Other people, they write that down things, you disappear from the internet a lot longer than you expected. So, doing a hard clear BGP is really the absolute last resort. But to solve this particular problem, you use something called soft reconfiguration. I've put a pretty graphic up here of what kind of happens that doesn't really. Basically, it's a clear, normal BGP process that comes to the BGP in process thing. That's where all your policy is done. The best path is picked. Everything goes to the BGP table, the best path is flagged. Best path goes to the following table. Best path is sent to the BGP out process to disappear. The soft reconfiguration, you keep a copy of everything that comes in. So everything you hear from your neighbor, you keep a copy of it. What's thrown away, well, you still have a copy there. So if you want to implement new policy and you're peering, you don't have to go to your peer and say, well, we're going to bring the whole session up again because I don't know what to send. The way all you actually do is you go to your BGP in table, you hear the entire announcement that your neighbor sent you, you run that through your filters, and you can update the BGP table quite in a straightforward fashion without affecting the BGP query at all. So this was like the first solution. This has been around for years and years, but it meant that you no longer had to do a hard BGP query. You didn't have to go to your neighboring browser and use that session. You can get a copy of what your neighbor sent you. So the new policies activated are taken down and restarting the session, which is good, configured on a neighbor basis. The big downside was to use more memory. Use more memory to keep prefixes, the attributes have been changed and are not being accepted. For example, you get a full feed and you want to change local precedent and say, on every single prefix you hear that full feed, that can double the amount of memory you need for that particular feed. It's like extra expensive.
Double. It's not quite double, but it's almost double. So for example, a full feed, what fits into 10 megabytes, so it would mean near enough 20 megabytes. Okay? From memory. Yeah, question?
Probably a little inappropriate for this one, but considering who you work for, it raises some serious questions about engineering that has 2 DRAM sockets and the previous version of the card is probably one socket, and they still are only charged $100 for a 60 meg equivalent, when today I can get a 112 meg DIM for well under $100. And if I had a full array of sockets even on your motherboard, you could tank it up to 4 or 5 gigs, but you don't have address because you can make it work. And it's not as though it's the first time. It's a history repeating over and over itself, over every time you run these processes.
I agree with you.
You can take it back.
I agree. Not much else I can say. The cameras are here, so it's... If the cameras weren't here, I'll tell you a lot more.
Wasn't your decision, right?
It wasn't my decision. Was there another question? Just an observation. Oh, okay. Right. But yes, it does use more memory. So this is a big downside. Was a very, very big downside to it. The way you configure it was basically soft reconfiguration inbound like that. The inbound is probably superfluous, but that's just the way it appeared in the parser. And then to reset the BGP session, you just do a clear and you specify the soft thing at the end. So that was quite nice. A lot of people requested this to be default, but I think that was people were being really worried about how much memory this could potentially take up in the router. Okay, much better way to do it is actually use the write refresh capability. This has been around probably for about a year or so. This is actually a much better way of doing things. Again, non-disruptive policy changes. You don't need to configure anything in the router. That's a plus. You don't need any additional memory. Okay, you don't have to go and buy expensive Cisco memory. It requires peering routers to support the write refresh capability. And that's documented in RFC 2918. Okay. And this time around, we just do a clear IP BGP in, for example. It tells the peer to resend the full BGP announcement. And what happens is your local router will send a message to the other one saying, please send me everything, and it will send everything over the link. So completely non-disruptive, nothing is affected, your traffic will pass on as normal. The only thing that has changed is anything that's impacted by your policy change. So this is really the best way of doing it. And it's hard work, certainly in my part of the world, to try and educate ISPs, use write refresh, use it. A lot of vendors support it now, so it's not just a Cisco strange thing as it was seen for a long time. A lot of vendors support this now, so there's really not much reason for not trying to use this. And I'm not saying it just because it's here, I'm saying it more for the sake of the stability of internet as well as the service provider network. So I'm sure a lot of you know if you bring down a full BGP session, what it takes in the router to bring this back up again. Okay? Right? And getting people to do, when they're resetting a BGP session, don't forget to use the in or the out command there. Okay, when to use soft reconfiguration, when to use write refresh. Always use write refresh. If the neighbor doesn't support the capability, then use soft reconfiguration. Right? But again, from looking around, about the only implementation that doesn't seem to support it is GateD, from what I see. So otherwise, yeah, write refresh should work between most implementations. Otherwise, use soft reconfiguration. Of course, some people like using soft reconfiguration because they like to see what they get from the neighbors before it's filtered. And if you want to do that, well, that's fine, that's fair enough. And the final line, only use a hard reset as a last resort, absolute last resort. Okay, the next thing, peer groups. Well, without peer groups, iBGP neighbors will receive the same update. Because you've set up a full iBGP mesh, you've set the same configuration for everybody. It means a large mesh takes a long time to build. I think today it's probably not so much of an issue, but certainly when the Motorola processors were in the routers, we could see iBGP mesh taking several minutes. 15, 20 minutes was not unusual in our network in the UK. So peer groups were certainly a lifesaver in that time because you calculated the update that went to the iBGP neighbor and it was sent once. Okay? You don't waste the router CPU and you means that the iBGP mesh builds very, very quickly. Okay? So, advantages, well, it makes the configuration easier. Many configuration error was made before peer groups were there. You know, when you're looking through long, long lines of code, it's very, very easy to miss out that one line that's breaking your entire backbone. Okay, so make configuration easier, makes it less prone to error, makes it a lot more readable, substantially reduces CPU load on the router, builds a mesh very, very quickly. Certainly when we were doing the comparison, you know, building a mesh in 30 seconds compared with 15 minutes was a big win for us. Okay? It only applies for outbound. Right? Peer group only really applies for outbound policies. So that means that members of a peer group can have different inbound policies. And you can use them for eBGP neighbors as well. It's not restricted to iBGP. Question?
Is the capability to tweak the peer group announce and outbound supposed to be there? Like, for instance, if you've got an outbound order from eBGP neighbor for a full view of some kind, to add a default route or to add an additional.
You can tweak the peer group, but
I've tried it and it hasn't worked.
Okay.
So I just didn't know if it was supposed to be supported.
I don't know the answer. No. But I can find out. Sure. So configuring it for iBGP. I suppose the nice thing is your iBGP configuration is all clumped up at the beginning, and then you can just apply it on a per neighbor basis like that. Notice you can still have your own inbound policy like that. Okay, so this is a typical example of configuring the peer group. Next question?
I apologize, I'm a little unsure on the
Okay, the peer group is used for grouping configuration that's the same, right? So say in your network you've got 20 routers, they all have the same, same configuration for each neighbor, right? So if you just look through the configuration, router 1 will have, remote AS, update source, send community, maybe a route map. For these 20 routers, you've got to type in this thing 19 times. Right, that just gets painful. You can make mistakes, miss things out. The router has got to calculate the update that it has to send. Updates every minute. It's got to calculate those 19 times. It's much more efficient to put it all in one thing like this. It does the calculation here once, and then it's just sent out to everybody who belongs to this. So as you have a very, very large iBGP mesh, this really reduces the CPU impact on the router, as well as all other reasons I've listed. Okay? So it's quite important to do this. For external neighbors, you can do the same thing. Peer groups can all be listed here. You just specify the ASs separately in a line like that. And again, I always encourage people to try and use anything that makes it more efficient to save memory, save CPU, make the configuration more readable, whatever equipment you're using. Right? It's a big advantage to have a simplicity in the configuration. Right, route flap damping. Route flap is the going up and down of a path or a change in attribute. BGP withdrawal followed by an update, that's a flap. Right? The prefix is being announced and it's there in your network, then you withdraw it, and then it's re-announced, that's a flap. Okay? Notice an eBGP neighbor going down, up or down then up is not a flap. That's like the physical link between you and your neighbor goes down, that isn't a flap. Okay? It's only when you hear an announcement that says withdraw this prefix, and then re-announce this prefix. Okay? This ripples through the entire internet. Okay? If you withdraw a prefix, every router that's carrying the full routing table will eventually hear this. It wastes CPU. It's a big, big issue, certainly a few years ago, the amount of flaps that are going through the internet. I think with the bigger CPUs and the routers now, it's not so much of an issue, but I think it's still very important. The aim of damping is to reduce the scope of the flap propagation. Right? So, it's documented in RC 2439. Skip this one. The way it works is we add a penalty for each flap. So, penalty is 1,000, for example. A change in attribute gets a penalty of 500. Again, this implementation. We want to exponentially decay the penalty, so half-life time is used to determine the decay rate. Penalty above the suppressed limit means we don't advertise the right to our peers. Once the penalty has decayed below the reuse limit, we then re-advertise the route to our peers. And then the penalty gets reset to 0 when it's half the reuse limit. In other words, all flap history is just wiped out. That's basically how it works. The picture looks something like this. Okay, prefix being announced. This is the time axis for a particular time. It flaps. It attracts a penalty of 1, and then the exponential decay will start immediately. Right, so we have the exponential decay, it flaps again, decay, flap. The penalty now takes it over the suppress limit. So the prefix is now no longer announced to any neighbor. Carries on flapping until somebody figures out that something's broken or to fix whatever needs to be fixed. And then we have all the exponential decay until we reach the reuse limit, which is, well, 750 is default. Reaches the reuse limit, and then the network is re-announced. Okay? So basically, while the prefix is flapping, the network is not announced anywhere else. So other routers in the backbone are spared the updates and withdrawals and updates withdrawals. They don't have to recompute based on the flapping prefix. Okay? Notice suppress limit is here, reuse limit is there, and with an exponential decay. So once a prefix is suppressed and stops flapping, it can be quite a long time before it's actually reused within the network.
Can you give us an idea of what you've seen among the ISPs you work with, the common amount of time?
Okay, an example of common amount of time for how long prefixes have disappeared?
Yeah.
30 minutes upwards. If you're using, again, a couple of slides on, using some of the recommended parameters I've got there, yes, it can be 30 minutes upwards. Or if you just switch it on using the Cisco defaults, 30 minutes upwards. Between 30 and 60 minutes generally. So it is a long time. Okay, so, right. I suppose an important point to note here is flap damping only applies to the path that is flapping. Some people think, well, if I switch it on the route, that means it will cut me off from everything. It only affects the path that is flapping. And it only applies to eBGP peers. It doesn't apply to iBGP. It would be a bit silly if it was in your internal network. Well, the defaults are there. You can do fixed damping, configured like that, or you can set up selective damping based on a route map. Recommendations for ISPs, well, the community, certainly in Europe and some US ISPs, helped to put together this document, RIPE 210, which is actually being rewritten at the moment. I posted the rewrite to the list a couple of weeks ago, because one of the parameters doesn't actually work. So RIPE 210 are the recommended values. Some people considered the Cisco defaults were too aggressive, because they only allowed 2 flaps, and then on the 3rd flap, your prefix was suppressed. The RIPE 210 values allow 3 flaps and then suppression. And it's more aggressive for /24 flapping, which are 60 minutes suppressed, versus 22s and 23s, which are 45 minutes, and everything else, which is 30 minutes. Okay, best to read the document for the actual numbers. So the RIPE 210 values are a lot less aggressive than the defaults. So if you're using the defaults at the moment, you might want to consider using these instead. Okay, you need to be careful when setting parameters. It's the usual thing of you can type in any old numbers and they'll be taken. This was the bad one in RIPE 210. This one doesn't actually do anything. The reason is that the maximum possible penalty is 3,000, and that is the suppress limit as well. This value is the suppress limit. Right, that's the half-life time, that's the reuse value, and this is the maximum suppress time. Okay? You use the maximum suppress time and the half-life and the reuse time to calculate what the maximum penalty is. Right? So what we're really saying is at 60 minutes we should have a penalty of 750. So if you use the half-life concept at 30 minutes, it doubles it, okay, to 1500, and a half-life later it doubles 1500 to 3000. So the maximum value of the penalty can ever be is 3000, which is also the suppress limit. And if you actually try this out in real life, you'll find that you have about a 1 in 100 chance of getting any prefix to dampen at all, which is a bit of a shame because this one was aimed at the /24s. Okay? This example works nicely. The maximum value of the penalty here can be 8,000. Okay? So if you're cooking your own parameters for flat damping, make sure they make sense. Okay? Well, that's not documented anywhere, but that's the way you work it out. Figure out your maximum suppress time you're going to use, the half-life time, the reuse limit you've set, and then that's the maximum value the penalty can be. Okay, so make sure that value is substantially less than the suppress limit. That's always the good advice. Okay, route reflectors, confederations. Well, scaling IBGP. Okay, IBGP with 20 routers, you can run the full mesh. 100 routers start getting a little bit interesting. Well, in this case, 13 routers, you've got 78 IBGP sessions. 1,000 routers, you have nearly 500,000 IBGP. Right? I mean, that's just not scaling. This is an n-squared scaling problem, and that's just no good. There are two solutions to this problem. One of them is a route reflector, which is generally quite simple to deploy and run. Another one is confederation, which is quite a bit more complex and has only corner case benefits over the route reflector. So we'll have a quick look at these two. The way the route reflector works, well, you've got an eBGP session in router B. He passes prefix to router A. Now, if you're on the full IBGP mesh, well, B will have a full IBGP with C. Then B will pass the prefix as it lands onto C as well. But if you don't do the full IBGP mesh, you want to implement a route reflector setup instead, you want to change router A. Because router A in the full mesh won't take any prefixes it learns from B and pass them on to C. It won't do that. If you make router A a route reflector, then it'll take everything it learns from B and pass them on to C. So you're changing this must not pass on IBGP prefixes. That's all the difference there is between a normal IBGP speaker and a route reflector. Okay, so the layout in the network could be something like this. You've got your route reflectors in the core, you've got your clients scattered around the edge. Reflector will receive path information from clients and non-clients. So receive something from the client, it will pass it on to non-clients and other clients. If it sees something from, say, B and C, it will pass it on to the clients, and so forth. Okay? So it's just a simple way of changing how the IBGP behaves. You can have all the clients just pointing to the reflector, or you can fully mesh the client as well if you want to. Okay? So there are two ways to do it. Most ISPs just do this. They'll have the IBGP sessions just pointing to the reflector. If you want to read about it, it's described in RFC 2796. The way to do the topology, divide the backbone into multiple clusters, at least one route reflector and a few clients per cluster. Route reflectors need to be fully meshed. They're just normal IBGP speakers for the rest of the network. It's just the clients see them as something different. Clients in the cluster could be fully meshed if you want to, but very few people do that nowadays. You don't need to touch your IGP. Just leave your IGP alone. So OSPF, ISIS, whatever, you can just leave that, which is a big advantage. For loop avoidance, well, a couple of new BGP attributes were added. First one is the originator ID, which carries the router ID of the originator of the route in the local AS. And then you've got the cluster list attribute, which is a little bit like the AS path, but it lists the route reflectors that the prefix has passed from. Okay. Cluster ID is added when the update is sent by the route reflector. Cluster ID is automatically set from the router ID. So if you're using loopback interface in the router, well, the router ID will come from that. So the cluster ID is set from that. Do not use the BGP cluster ID command. Too much documentation says this is a good thing to do. I'm afraid the documentation is wrong. Okay, you can just land into so much trouble using the cluster ID like that. Redundancy. Multiple route reflectors can be configured in the same cluster. This is actually not advised. And again, this goes counter to a lot of documentation that exists. All route reflectors in the cluster must have the same cluster ID. Right? Otherwise, it's in a different cluster. The problem with this is you can end up with fairly substantial and bad routing loops and black holes. I think we've put enough examples, certainly on the Cisco web page, of how this can go badly wrong. So, what most ISPs, I find, have always been doing is this thing. A router may be a client of route reflectors in different clusters. Okay? So, for example, you may have two core routers and a point of presence. Each core router will be in a different cluster, just by virtue of its router ID, and all the other routers in the POP will have an iBGP session with these two core routers. Right? You've effectively got two different clusters overlaid. Okay? And that way you get your redundancy. Yeah?
So effectively, you're able to have two replicas at the same time. They're both numerically less than themselves.
Yeah. How is this different from just having two route reflectors with the same cluster ID?
How can we have replicas with the same cluster?
I can't hear you now.
Imagine that because I've seen large networks
Yeah.
using that for a very long time, never had any issues with routing intercepts for the same time of the record like this one.
Yeah. Yeah, I mean, the question was just saying, he's seen large network working for a long time with route reflectors with the same cluster ID set. Yeah, sure, there are plenty that are working properly. But, I've found, and a lot of my colleagues have found, a lot of the new networks starting up, people are running route reflectors across vast tracts of network. They're not keeping it localized, they're not thinking about the design. They're just like, oh wow, route reflectors, let's just go and, they don't actually look at some of the original design intentions.
Now, I recall previous one was driving the cluster ID.
Yeah.
You draw the cluster ID off the loopback.
Well, it draws the cluster ID from the router ID,
Okay. So
wherever that's come from.
you've got two, if you're not using the cluster ID domain,
Yeah.
you've got two reflectors in the region, and they're really two different.
Two separate.
Logically, they're two separate clusters.
Logically, they're two separate clusters if you don't do it. That's right, they just got the same cluster. Yeah, there's a scenario which I don't remember off the top of my head, but it's certainly on the Cisco web pages where you can end up with a fairly significant black hole, where people basically had set up one route reflector in one point of presence and another one in another point of presence, separated by a long distance, and try and set the cluster ID the same, and ended up with a fairly substantial black hole. So, yeah. So I think it was trying to tell people that, well, this works anyway. So, unless you know what you're doing, understand what you're doing, there's little point trying to set cluster ID properly. This will work just fine. Okay. I mean, the picture is basically that. I mean, it looks the same. You're not setting the cluster ID there, and you effectively get two clusters. So cluster 1's in green, cluster 2's in red. It works the same way. You just avoid having any potential problems with a routing loop. But I never saw this as any issue at all. Basically, when route reflectors appeared in the iOS code back when I was at UNet, we configured this. We never knew anything better. Okay, and this just worked. And it was only when we got a review of the network being carried out by Cisco that they said, but you can't do this. This doesn't work. I was like, well, we've been using it for 2 years. What do you mean it doesn't work? And they tried setting the cluster ID, and it's like, well, it didn't do anything. There's no point. Right? But this had just worked fine. And the current thinking, if you look at certainly a lot of the current documentation now, is, this is fine. This works. There's no real win gained by setting the cluster ID. Okay, migration. I'm going to try and finish the route reflector and confederation bit, and then we can have a break, because that's a natural break in the slides. So migration, well, where to put the reflectors? It's really, really, really important to follow the physical topology. Okay. I don't have much view on how the North American ISPs implement the networks and so on, but I certainly know in Asia Pacific that people don't do this. They say, route reflectors, I'll put 2 in the middle of my network and that will do everything. And it's like, given some of the infrastructures that are there, having breakages in the backbone causes a lot of problems. Okay, so it's very, very important to follow the physical topology. I mean, if the network is not radial, then it makes no sense putting 2 route reflectors in the middle. My favorite way of doing it, you have points of presence around your backbone. It may be single layer, it could be 2, 3, whatever. Try and build the route reflector hierarchy to follow that, and then it just works very, very easily. Keep it simple. All right, so typical ISP network might be this. POP has 2 core routers the route reflector for the POP. You've got 2 overlaid clusters. Typical ISP network. Core routers of the fully meshed IBGP create further hierarchy if the core gets too big. Right? Nobody's asked the question, well, how big can the core be? Well, I don't know. It depends on the infrastructure, the type of routers, the type of network you're carrying. You know, how long is a piece of string? But you know, if you feel that your mesh is getting too big, create further hierarchy. You can nest route reflectors as deep as you like. Nobody's really found where it breaks yet. So that's why a lot of people say route reflectors scale infinitely. Of course, somebody wants to try and prove that they break, then let us all know. Configure one cluster at a time. This is by migrating to them. Eliminate redundant IBGP sessions. And it's actually quite simple. When I migrated our UK network in one maintenance slot, which is extremely bad practice because that's against all the things that would be preachers, but it was just so simple to migrate them. Okay. So migrate small parts of the network one at a time, and it makes it quite easy to do. Again, setting them up, there's only one thing you need to do. On the router, which is being the route reflector, you have a one-line command which says route reflector client, and that states that this router is a client of this particular neighbor. Okay. Okay, configurations. Just a few slides. I'm not going to go through them in much depth. The way this works is by dividing the main autonomous system into lots of sub-autonomous systems. Okay. So rather than running IBGP mesh, you break up your network. Within each sub-autonomous system, you run IBGP and you run eBGP between the sub-ASs. But it's not quite eBGP. You're keeping some IBGP information. Some people call it eIBGP. Again, it just depends which service provider you are. You want to preserve next hop information across the sub-AS, because IBGP carries this, and preserve local preference and MED as well. As with route reflectors, you can just use a single IGP for your entire AS. Latest RFC is RFC 3065 that describes confederations. It's visible to the outside world as a single AS. So as far as the world is concerned, you're just a normal autonomous system doing normal things. And this is this confederation identifier thing. Each sub-autonomous system will use a number from the private AS space. So that's 64512 to 65534. So 1024 ASs available there. So you can split your confederation into 1024 ASs if you want to. IBGP speakers in the sub-AS need to be fully meshed. Okay, so it just looks like lots of ISP networks joined together by eBGP. Total number of neighbors is reduced by limiting the full mesh requirement to only the peers in the sub-AS. So it makes your IBGP mesh scale somewhat better. Picture would look something like this. Here's AS200, and he split his network into 3 ASs. These 3 sub-ASs, your configuration on router B could be something like this. You set up your confederation identifier, 200. That's your real AS as far as the world's concerned. You list your peers. Here, your neighboring confederation ASs, you list them here. And then just list your neighbor commands for the eBGP sessions. So again, it's quite simple to set up a confederation. The route propagation decisions, well, same as with normal BGP. If it's prefix comes from a peer in the same sub-AS, it's only sent to external peers. If it comes from external peers, it's sent to all neighbors. Right, so it's normal eBGP rules. External peers refers to peers outside the confederation and peers in a different sub-AS. But notice, local preference, MED, and next hop are preserved. That's the major difference. And the output, well, could look something like this. The AS path, the confederations are put into brackets, like that. Okay? So that's the only difference from regular BGP. You see confederation ASs in standard brackets like that. Okay, this is another of the frequently asked questions that I get anyway. Should we use route reflectors or should we use confederations? Well, comparing the two, confederations can have internet connectivity anywhere, in other words, eBGP connections anywhere, as with route reflectors. Gives you a multi-level hierarchy, the scale pretty much as far as we know. Gives you policy control with both of them. But the scalability configurations, you're probably limited with by your topology and by the number of ASs that you have. As with route reflectors, nobody really knows where the end is. Migration complexity, going to confederations from a standard network is really hard. You have to remove the standard BGP configuration and put in the sub-AS configuration. Having been involved in one of these, it is difficult, whereas migrating to a route reflector is just, 10-minute job. So you find that most service providers today, those who are using confederations stay there, they're quite happy with them. New guys who are coming here look at confederations, they look at the existing deployed things, they look at route reflectors, and pretty much 90% of the time they choose route reflector to do it because it is much, much simpler.
So, you find the stopping point. We have a break for 3 to 3:30.
Yes. Stopping point is 2 slides. Okay, what other good things about confederations? Well, you can ease absorbing of other ISPs into your network. So if you're on the acquisition trail, it's quite easy. If you've got a confederation in your network, you just make their network part of your confederation. But you can use the local AS feature as well. I'll cover that in a bit. You can use route reflectors inside a confederation to reduce the sub-ASI BGP mesh. You can do that as well. So, I think I'm not going to try and say which one to use. You've got a lot of people who argue positively for both cases. But as far as I can see, both will pretty much scale for a long, long way for most applications. Okay, so those are the 4 techniques. So they should be part of all ISP networks. And that's it. Let's have our break. I'll start again at 3:30. I'm sorry for stealing 10 minutes of your break.
BGP and ISP network. Current practices. These are current practices, current best practices. I've covered a lot of this from just looking at configurations and private networks. From the work experience, what I've been doing, what colleagues have seen. Just taking general best advice from the industry. Okay, so there's BGP and there's also OSPF and IFI. Right. These are interior routing protocol, IFI and OSPF. These are the 2 main ones that we use in ISP networks today. They're used for carrying infrastructure addresses.
Interesting enough, I find a common problem today is ISPs starting up. They go read the books, and the books tell them everything goes into OSPF. And we've got so many horror networks running around there with 12,000 prefixes in OSPF or ISIs. This does not work. It does not scale. It breaks an awful lot. Okay? So, really important. Only carry infrastructure. In other words, things like loopback interfaces, point-to-point link addresses. That's pretty much all that should be going into the IGP. If you can count all your infrastructure links and all your routers, you know how big your routing table is going to be. Right? You should not be carrying internet prefixes or customer prefixes in your IGP. Right? Any extra overhead just slows the IGP down, makes convergence slower, makes the failover slower when the link failures, and you don't want that. Okay. BGP is used internally and externally. Use iBGP to carry some or all of the internet prefixes across your backbone and to carry your customer prefixes. Okay, that's current best practice today. eBGP is used to exchange prefixes with other ASs and implement your routing policy. Do not distribute BGP into IGP. It won't fit 105,000 prefixes when I looked yesterday. That won't fit into ISIs or OSPF. Don't take IGP routes into BGP. IGP is generally a lot more unstable because it's your infrastructure. So you don't want all the IGP changes being propagated into your BGP and give resulting instability in the BGP. You want to keep a very, very clear distinction between BGP and your IGP. Don't use an IGP to carry customer prefixes. I've fixed 6 networks now who are doing the 12,000 prefixes in OSPF thing. And it doesn't work very well. Basically, well, the last one I did, if it had a link breakage, it would take about 5 minutes to find the next alternative path. Right? And that is not a very reliable network. Okay? Basic thing is your network will not scale if you do this. Okay, aggregation. ISPs will receive address block from regional registry, ARIN, or upstream provider. Aggregation means announcing the address block only, not sub-prefixes. Okay, sub-prefixes should only really be announced in special cases. Special cases that refers to is basically multi-homing, right? And even then, only judiciously. Aggregate should be generated internally, not on the network borders. This is another common mistake. People have designed the network all nicely, they set up the border routers, they generate the aggregate on the border. Now, this probably doesn't apply so much to a North American audience, but anybody overseas who puts equipment here in the States to connect to the US internet, well, they generate an aggregate on, guess where? The router which sits in the States. The circuit across specific breaks, it's still generating an aggregate, and, well, they black hole the entire traffic. Okay, so generate the aggregate essentially. We generated the aggregate in our UK network, UUNet. We generated the aggregate in our core routers in each point of presence. That worked fine. It's 2 routers per pop. That was the best way to do it. It's easy to configure aggregation. You set up network statements on a static route to null 0. That generates the aggregate. The reason I put this in so blatantly is a lot of people say, oh, well, it's really hard to generate an aggregate. It's much easier just announcing all the prefixes as I assign them to customers. I'm like, what's hard about those 3 lines? Really nothing hard at all. Or you can do it this way. There's even a command, aggregate address. Okay? Again, iOS specific, but there's an aggregate address command that generates your aggregate for you. It sets the aggregator attribute. It's all you really need. If you want to use the summary only thing, I've never used this. It will strip out all the specifics from the announcement. Okay? Announcing the aggregate. Well, this isn't hard either. Just make sure your prefix filter list includes your aggregate. And it's very, very simple to do. IP prefix list, permit your /19 or whatever it is. Okay? And just have neighbor statement with the prefix filter put in there. So it's a simple way of announcing your aggregate. Okay, ISPs who don't and won't aggregate are held in poor regard by the community. I think that's fairly safe to say. Registry's minimum allocation size is now /20. There's no real reason to see sub-prefixes of allocated blocks in the internet. But there are more than 60,000 /24s. There was 61,000 this morning. That is quite a lot. If anybody looks at Tony Bates' CIDR report, you can find out how this can get a lot better. Okay? There are a lot of ISPs, several who should know better, who are just announcing 24s. Why are we announcing 24s? What use for 24? Rather than trying to announce aggregates from this. If you're giving address space to your customers, coming out of the aggregate block, that's all you really should be announcing. Okay? Okay, receiving prefixes. This is, again, more good practice stuff. ISP should only accept prefixes which have been assigned or allocated to the downstream peer. For example, if the downstream has a 220/50/20 network block, that's all that he should be announcing to his peers, and that's all the peers should be accepting from that. Right? So again, standard configuration. So a configuration example might be something like this. On the upstream, from your customer, well, they're going to accept /20. If your customer wants to do something different, well, he has got to tell you, or he's got to ask you. You've got the option of charging him money for it. Okay? But I'll try and recommend by default only accept the aggregate that the customer is entitled to announce. Receiving prefixes from your upstreams. Well, it's not really desirable unless it's very, very necessary. Again, the special circumstances, multi-homing, which we'll cover a little bit later. And even then, what you receive from upstream, you should control quite tightly. It's much better to ask the upstream to either originate a default route, okay, send you the default route, or announce one or a few prefixes which you can use as a default route. Okay, there's no status symbol to carrying the full routing table, quite honestly. Some people like doing it. Well, it's okay. You can carry 105,000 prefixes. The vendors will quite happily sell you all the routers and memory to do that, but quite often it is not necessary. People who have seen parts of this tutorial in Asia Pac have gone home, they've thrown away the full routing table, and they're quite happy with what they've actually got. Okay, so receiving prefixes from your upstream, prefix list, in, filter in. You only want to hear the default from your upstream, so you accept the default from them. To your upstream, only send your aggregate to /19 or whatever it is. Okay, and on upstream, well, your default originate. That will send the default to your customer. Prefix list customer in. You only permit the aggregate from your customer. Outbound, only make sure the default goes there. Okay, so this is the nicest way of doing it. This isn't really a made-up configuration. When I actually used this stuff in my own days at UNet, this is the sort of stuff that we did. Okay, customers are quite clear. BGP customers got a default originate. If they wanted something more, it was show us your money. Well, it was in the UK anyway. Okay, if it's necessary to receive prefixes from upstream provider, be careful. Don't accept RFC 1918, private address space. Private address space should not be connected to the internet, etc. Bill Manning's draft lists RFC 1918 addresses and a few others, but shouldn't appear on the routing table. So if you want to know why and wherefore, it's there. Don't accept your own prefix. How many people forget that? So many do. Okay? Don't accept your own prefix or any subnets of your own prefix. Really important. Don't accept the default unless you need it, unless you know you're going to get it from your upstream. And also don't accept prefixes longer than /24. That was probably a bit more contentious, but I'm one of the people who believes that the boundary should be enforced at /24. Jeff Houston at the recent, well, in his presentations that he's done recently at IETF, has said, well, you know, any size should work on the routing table. Side is broken. But that's probably the opposite view. Okay, so an example of a prefix list might be something like this. Block your default, network 0, 10, 127, 169.254, the DHCP auto configuration address, 172.16, 192.02 is a test network, 192.168 private. Here's your own address range, 22110 /19, but notice all prefix lengths are blocked. Okay? You don't want anybody taking your address space and announcing it back to you in ever decreasing fragments. Right? I mean, people can attack networks by announcing sub-prefixes into the BGP. And of course, these sub-prefixes override anything you've got. So, block your network coming from the outside. Block multicast. This is a unicast BGP, so you don't want to hear any multicast addresses coming through there. 25s and longer, we want to block, and then we allow everything else in. So this is very, very typical BGP configuration pointing towards your upstream. Okay, putting prefixes into IBGP. Okay, as I said, IBGP carries customer prefixes. Don't ever use the IGP. Point static route to customer interface. Use a BGP network statement. As long as the static route exists, interface is active, prefix will be in BGP. So it might look something like this. Again, this is lifted and numbers changed from what I've done in my past. We use IP unnumbered on the serial point-to-point link, so we didn't have to carry the /30 point-to-point address around our IGP. Kept the IGP small. So loopback configured, IP number for loopback. We point to the static route for the customer at the serial interface, and then BGP with the network statement, and that was it. Quite easy. So the customer /22 in this case went into the IBGP. Okay. One thing to note is there's an interface flap. It will result in the prefix withdraw and re-announce. If the interface flaps, in other words, goes down, the static route disappears. Static route disappears, there's no entry in the routing table, so BGP will withdraw the network from the BGP table. So you could potentially get a routing flap within your backbone. You only announce an aggregate to the internet, so this sub-prefix won't appear on the internet, but it still will appear in your backbone. And you should be always very, very mindful of BGP instabilities in your backbone as well. Right? So try and aim for stability in your backbone. One thing you can do with a static route is put a permanent option on it. And that will make sure the static route was always in the routing table, even though the interface goes down. Okay? In fact, I would recommend people do this. There's no real reason not to. Okay? Many ISPs use redistribute static rather than the network statement. Okay? But again, I only recommend people to do this if they understand why. I've seen a lot of accidents with redistribution. People just do redistribute static, and every single static route they have ends up in BGP. They don't have the filter set up properly, so it ends up in the internet. Those of you who have seen the routing report that I send every week will probably notice one or two funny prefixes that appear in the BGP table. And when I send email to those ISPs saying, where does this come from? They say, I don't know. I say, oh yeah, bogus static route. Somebody was setting up something in our test lab. It's like, well, how can a static get into BGP? Because they've done the redistribute without thinking properly. Okay, so care with redistribute, as I said. So an example might be something like this. Always use some type of filtering on the redistribute. So I've got redistribute static route map, static to BGP, so we match IP address prefixless ISP block. So the range of addresses that we're using or assigning customer address space out of goes in the prefix list here. We set the origin IGP so it looks like a BGP network statement, and then this will work fine. Again, this is just lifted from my past. Okay. Now, what else? Yeah, and this is pretty much what I said. The route map can be used for setting communities and other attributes, setting origin code, and so forth. So just be careful with this. Now, configuration tips. Make sure loopback is configured on router, run IBGP in loopbacks, as I said earlier. Make sure the IGP carries loopback/32 address. If you don't have it in the IGP, then you can't set up IBGP between the routers. Make sure the IGP carries demarcation zone networks. Okay, this is a classic problem. You don't carry the demarcation in the IGP, the router can't get to the edge. Right? You can't see your next hop. So even though everything looks okay, you can't get outside your backbone. Alternatively, if you don't want to carry demarcation in your IGP, you can use something called next hop self on your IBGP neighbors. Okay, next hop self, something like this. It's used by many ISPs. A lot of ISPs use next hop self rather than carrying the demarcation /30 in the IGP. So connecting your customers or connecting your eBGP neighbors, rather than having this /30 running around in your IGP, we use next hop self. And that means the announcement of the customer prefix goes with the next hop address of the local router, rather than the point-to-point link pointing to the customer. Okay? It's an alternative to using IPN number. I mean, I used IPN number because it was, well, it just saved address space, and we could tell RIPE NCC were doing this and they were happy with us. But yeah, it's two possibilities. Again, helps scale the network because your IGP really only has infrastructure and the loopbacks in it. You don't have your customer point-to-point links appearing in there. Okay, I've put in a BGP template, just good things to do for setting up your iBGP. And again, I know this is iOS specific, but the principles apply to everything, everywhere. Right? Try and set up a template. Make everything template-based rather than a homebrew configuration for every single router. If you work by templates, it becomes very, very easy to reconstruct things, very easy to add new equipment to your backbone. So in this particular example, well, I'm using a peer group for my iBGP. The remote AS goes in. I use a description line, so when I look at the configuration, I know what it does. Loopback goes in there, next hop self. So I use that for my iBGP. Send community. Send community should be default for iBGP. You should carry communities within your backbone. Version 4, yes, that's being super paranoid, but it's still probably a good idea to put version 4 in there. Password, very, very, very necessary. Can't overemphasize the importance of that. If you're not using password for your iBGP or eBGP, you seriously should be considering it. I've seen a lot of well, evidence of denial of service attacks against BGP, simply because people don't have passwords on there. Right, so make sure you put a password in there. Okay, so that's a sort of template you want to use. This is simplified. Most ISPs tend to have 3 or 4 different iBGP configurations, depending on what they're doing in the network. So that's really what I've talked about. eBGP peers, well, again, try and set up a default configuration template. Right, this is for my peers. So we put in some damping, so I'm using the right 210 values rather than the defaults. Then we set up a peer group for external neighbors. So this is one for AS200, again, description. Remove private AS. Again, that should be a default in any eBGP session an ISP has. A lot of ISPs are using private ASs for various things, as we'll see a bit later. And you'd be surprised the number of private ASs that leak out into the global routing table. Right? I think the last count there were about, well, in my view, I was seeing about 6. I'm seeing 6 or 7 regularly. Some days it's gone up to like 20, 50. Okay, it's quite a bit. And it's usually because somebody's forgotten this command. It's like, yeah, just put in the template. If it's template-based, then you're always putting this onto every single new peer. You don't have a problem. Again, version 4 for being paranoid. Put in a disaster filter in case you break your route maps. Do the real filtering here. Again, password, really important. Agree a password between you and your peer that can be used. Maximum prefix, again, quite important. If you only expect to get 10,000 prefixes from your neighbor and he accidentally sends you the full routing table and your router's only got memory for 15,000 prefixes, it could be a bit of a problem. Right? If you can do the maximum prefix tracking, then the router will send you messages saying, look out, I'm starting to get a full feed here, running out of memory and so on. Okay, so this is actually really useful. Again, should be a mandatory command for eBGP sessions. Okay, and then neighbor, you just apply the peer group to the neighbor. Again, try and understand how using templates actually makes life a lot easier for configuring things. Okay. So that was just what I said. Also, log neighbor changes. This actually gives you a detailed log of things that happen. Networks can really never have too much information. The router can produce you a lot of information if you want it. Right? So log neighbor changes, which probably is default by now. But again, that will display messages of things that have changed, why the neighbor's gone down, why the neighbor is not coming up. Could be password mismatch. All these things are displayed. I've seen people sitting there scratching their heads, BGP's not coming up. Or BGP went down, it won't come back up. Well, look at the log. The logs don't have anything because they don't have the log neighbor changes on. Also, enable deterministic MED. I'll cover a problem with MED a little bit later in the troubleshooting part. Otherwise, your best path could be different every time the BGP sessions reset. Okay? You want to use the deterministic MED. Also, this one, I've never really pushed this hard. I mean, we did this in the UK, but I've never pushed this one very hard. But make the administrative distance of BGP higher than that of any IGP. Okay? eBGP admin distance is 20, for example, OSPF 100 and something. You don't want external or BGP prefixes overriding what you hear in OSPF. Right? Accidents can happen with that. So again, just move the distances away up to 200 or something, and you don't have accidents coming from outside your network. Again, if you're filtering properly on the edge, this should never be an issue. But it's good to build in more than just one layer of redundancy in the network. Customer aggregation, well, BGP customers could, for example, you could offer 3 types of feeds. Again, it's easier than a custom configuration per peer. You can sell this as 3 types of services, right? Use communities to determine the 3 different feeds. Static customers, again, use communities. And you can differentiate between different types of prefixes using these communities. It makes your eBGP filtering really easy. So, just walking through an example. Define at least 3 peer groups. For example, a customer default, where you only send the default route to the customer. Cust, send customer routes only, in other words, just your backbone IBGP prefixes, or cust full, send the full internet routing table. You could sell these as different services. You could charge different amounts of money for it. Right? Identify routes via communities. For example, this community 100:4100 are all your customers. 100:4500 are all your peers. So all prefixes coming from your customers go in there. All prefixes coming from your peers go in here. And then when you're filtering elsewhere on the edge of your network, you filter according to these communities, rather than trying to keep AS filters up to date, prefix filters up to date, and anything else up to date. Right? It's really, really hard. I always say to people, we should have seen our configuration before communities existed. It was easily one of the wildest bits of configuration I've ever seen. Right? With communities, it became beautifully simple. Really, really simple. Apply passwords per neighbor. And you should be doing that now. Apply inbound, outbound prefix list per neighbor as well. Always filter them. So something like that. It's just a pretty picture for example. Using route reflector, you can send different peer groups to different customers, like that. What about static customers? Again, you can use communities to identify different routes. For example, 100:4000. These are your customers who are getting address space out of your address block. Put them into that community. Sorry, these are your address blocks. These are your aggregates. 100:4200. Customers who've got address space from your block. 100:4300. Customers who get address space that's not part of your block. So address space could come, could be their own address space, legacy address space, whatever. Okay, but they're not part of your block. All this will help with aggregation, IBGP, and filtering. Okay, if you're going to carry the full routing table across your backbone, you might want to carry it in the core of the network only, and not an aggregation part of the network. Right? If you've got these different communities doing different things, then you just filter your IBGP based on community. You don't have to set up convoluted filters and prefix lists everywhere. You just filter on community. I haven't put any examples in here. I mean, that would just take too long and be too complex to explain. But if you want to see some particular examples of doing this, I can give them to you. Okay, so how would you use this? Well, in your eBGP peers and upstreams, you send communities 100:4000. Remember, that was your aggregate. You can send 100:4100, which was what was that? That was your BGP customers, because they're obviously going to multi-home to you and somebody else, so you want to announce them to the internet at large. 4300 were your customers who've got their own address space. Okay, so you'll need to send these communities. You no longer have a prefix filter on the edge. You have a community-based filter. Lovely, easy. What about IBGP? Well, for full routing table, just send everything. And for a partial routing table, which you want to send to the edge of your network, or routers that can't handle the full routing table, you just send these communities. So you just match in all these communities, block everything else. Okay, so the typical routers would be your edge, aggregation, peering routers, exchange point routers. All of those you don't want the full routing table on there. And it makes configuration really simple. Acquisitions. Your ISP has just bought another ISP. How do you merge the networks? Well, it's not that easy, but you've got two options to actually make it work fairly quickly in the first instance. First option is to use confederations, make their AS a sub-AS of yours. Okay? Just make it part of your confederation. But if you're running a confederation, that's fine. If you're not, well, there's no point converting to confederation just to do this. So if you're not running a confederation, you can use the local AS feature where you can get the local router to masquerade as somebody else, as the ISP you've just bought. Okay? And it just looks something like this. Router A has got a process ID of 100, so he sits in AS 100. But as far as router C is concerned, he really looks as though he belongs to AS 300. And router A has just got this simple configuration, neighbor, local AS 300. So the announcement he sends out, he just adds in AS 300 into the AS path. Okay? So the peering with AS 200 is established as if router A belongs to AS 300. Router C here thinks he is peering with a router in AS 300. Okay? He thinks he's peering with a router in AS 300. And then This is fine for the initial phase, and then once you want to properly sort out relationships and all the rest, here, and then AS100 takes over the relationship. Out here, you can then change things to get the direct peering. But this will let you do the quick assimilation thing without anybody really noticing. Then you can come back and do the political stuff later on. Okay, if you look at the AS path, well, routes originating 100 look like this. Routes received from AS200 look like that. So it's exactly the same as it was before the acquisition. Okay, let's have a look at trouble and troubleshooting. So the first bit is looking at potential trouble spots and how to keep out of them. And then the second bit, the one or two common problems that colleagues and I have come across. And I don't know, when Sue asked me to do a troubleshooting bit for BGP, it's like, how can you do that? This is a day, it could take a day quite easily. So I've given you some common trouble spots that I've seen. And well, we'll see how we handle them. First one, you want to try and prevent GRE tunnels. Basically, people stealing your bandwidth. Right? Again, the colors haven't come out well at all. Hope you can see it. But this is the issue of carrying your demarcation point-to-point link in your IGP. Okay? You've got 511 and 5112. This is the point-to-point network. This is the peering or exchange point. AS2 carries a point-to-point link across the backbone. So any prefixes learned from here are visible in AS1. So if you look at this particular configuration, router E sets up a tunnel here, pointing to router B. Well, the IP address of the tunnel, 6001, pointing somewhere over there. Tunnel source is 6012, here, right? This point-to-point link. Tunnel destination 5112, we're saying there. Okay? And then we have a static route for 5112 pointing to 6011. Because AS2 is carrying this LAN across its IGP, notice IGP is carrying that LAN across its IGP, router D knows how to get to 5112. So this static route that's set up here pointing to router D actually works. So router E can see 5112 on router B. Okay, tunnel destination 5112. We know how to get there. Router B can do the same thing. We can set up a tunnel, address 6002, source 5112, pointing to 6012. Because AS2 is carrying this point-to-point link across his IGP, router C knows how to get there. Right? So B can just point a static route to C, and he knows how to get there. He gets his tunnel. So this AS can send traffic over this exchange and through this autonomous system quite easily without actually having any direct relationship. Right? Really important. Don't carry exchange point net in the IGP. Very, 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 very important. Okay? Use next hop cells. The second one. Nobody's really aware of this one, but the participants of the Links exchange point in London a few years ago were bitten quite severely by a pretender ISP who basically stole bandwidth from the 4 ISPs who provided the links with a view of the full routing table. Because we were all sweet and innocent and naive in those days, and we didn't think anything better to do. What happened was, this border router, router C, carried the full routing table. Or in a couple of cases, it carried just a default route that pointed back into the core of the network. Of course, if this guy's got a full routing table, or he's got a default, he knows how to get to the internet. If you've got a peering relationship only with AS1, and you've got this guy who comes along, you don't have a peering relationship with him because you just don't, he's too small or whatever. If he points a static default route to your router C, he can send all his outbound traffic that way. He may have a 64K circuit to the internet, or 56K, or dial up anything. And you've got a nice shiny OC12 sitting in there. He can point all this outbound traffic that way. Right? And if he's a content hosting site, which what do these people tend to be? It can be a lot of outbound traffic. Okay, inbound is not very much, so it can probably come in over this link. But outbound all goes this way. And you've got no way of spotting it. I last did this presentation, I think it scared about half the room. because they were present at exchange points and they were carried the full routing table there. This did happen to us in the UK. And it happened to the 4 ISPs who provided the links with a full view of the routing table. This is why having exchange point lines globally visible is probably not a good idea. Okay? So watch this one, really important. The way to guard against it, well, your exchange point router should not carry the full route or have a default on it. Only carry your domestic network routes in there. Okay? The ISP should not carry the exchange point NAP network prefix internally. Use next hop self, very important. Another way to do it, you can use RPF check for non-peers. Right? So you could carry full routes if you want to, but use an RPF check. Or use good filters for the peers. And then use something, well, NetFlow, packet sniffer, whatever, to actually try and spot anything that shouldn't be coming in. Okay? But it's easier simply just not carrying the full routing table and using the next hop self. Okay, auto summarization. These are two things which, yes, are iOS specific, but are really important that people are aware of, so you don't stumble across them. This one's historical, completely historical. It's no use whatsoever today at all. This one will automatically summarize sub-prefixes to the classical network. BGP will do that automatically by default without you asking. Okay, so for example, network 61.10.8/22 will appear on the internet as 61/8. Right? Aaron are giving address space out of, what's it, network 63 now? 64, 65, whatever. So you don't want to announce that /8 to the internet. Okay, I've seen it happen. So no auto summarization is a necessary requirement. The other one is synchronization, also historical, also a default in iOS, where BGP won't announce a prefix until it sees it in the IGP. Now, this is of no earthly use today in an ISP network, but again, it's another frequently asked question of, well, my route's in BGP, but I'm not seeing it being announced. Okay? So no synchronization is also very necessary. If you want the default changed, you know where to send email. Not to me. Troubleshooting. Right. Some common problems and solutions. So I'm going to have a look at, 3 problems. Probably quite straightforward ones, but they are frequently asked. First one is missing routes. It's the usual thing of, well, I see the prefix in BGP, but I don't see it being announced anywhere. What's going wrong? Okay? So you've got your network statement there, and it's like, well, why does the network not appear in the routing table? Well, not being announced by BGP. This network statement only puts an entry in the BGP table if an entry exists in the routing table. Okay? So you've got no entry in the routing table, then it's not going to appear in the BGP table either. So the usual thing is, people have forgotten the static route, the exact match static route. Okay, so the solution is put in your static route like that. Once you see it appear, you then get the entry in the BGP table. Believe it or not, this is actually quite a frequently asked question, which is why I've put it in. Route oscillation. This is a really, really common problem. Every minute, routes flap in the routing table from one next hop to another. For a large routing table, the most obvious symptom is a high CPU in the BGP router process. Okay, you see high CPU. BGP seems to be churning all the time. And it can be really frustrating, the problem. Never mind track it down. People just see it's like, BGP is consuming all my CPU. They don't know what's going wrong. Okay? Of course, if you've seen this before, you recognize the symptoms almost immediately. And then trying to track it down takes a bit of work to do as well. Diagram is this. We're going to concentrate on router 3. Router 3's got 2 paths to get down to AS12. It can go either this way, or it can go direct. Okay, so to try and remember the picture. Right, we do a show IP BGP summary. We don't really see anything unusual. Chopped out output a bit. Bit suspicious, the table version number is a bit high. That's a big giveaway. If a table version number on a couple of peers is racing away ahead, you see a lot of announcements from a couple of peers, then you've got to start worrying. Okay, something could be going wrong. There could be an oscillation there. Okay? So, trying to troubleshoot this. Well, have a look in the BGP table. Try and find, look in the routing table. Try and find a route that's only appeared very, very recently. So this one, 156.1/16, Well, it appeared there 53 seconds ago. Okay, that's recent. BGP things should be there for days, weeks, months, and so on. Right, so this one's appeared very recently, so something must be wrong. Right, so we'll do a show IP BGP on that network. We find it comes from two paths via AS4, originated by 12, and directly from 12, but it's marked as inaccessible. Right, so the first next hop is 1.1.1.1. The other one is 142.108.10.2. After the BGP scanner runs, well, to do a show IP BGP 156.1, we then see that the route points to 142.108.10.2. That's a few seconds later. And we do a show IP BGP. This is changed from inaccessible to the best path. So you've got the router switching from the path that goes via AS4 to going direct to AS12. Okay? And then you'll find a few seconds later, well, it could be a minute later, it'll switch back the other way, and then it'll switch to this one and switch back, and it'll oscillate back and forth like that. And you may not really notice anything. I mean, the outbound traffic may still all go roughly as is, or you may see taking one path one way and then another path the next few minutes. So, but what you will see is a high CPU. If you've got a full routing table oscillating like this will consume at least 50% of the CPU just to try and deal with it. Another symptom you may see, again depending on the setup, is your router may never actually get the full routing table loaded. And you may get like 3/4 of the way, then give up, and then start all over again. Right? It could be down to this problem. It usually is. Okay, so let's take a look at the next hop. Show IP route 142.108.10.2, known via BGP3. Oh dear. Right, next hop known by BGP. BGP next hops have to be known by another routing process. They cannot be known by BGP. So therein is the problem. Right, show IP BGP 142.108 has been heard from directly from this peering, from this router there, AS12. Okay. Oops. Next hop is recursive. The next hop has been heard by BGP. It cannot be heard from BGP. It's got to be heard by the IGP. In other words, the next hop has not been put into iBGP. This 142.108, wherever it is, 142.108.10.2 network should appear in the IGP that's running on this network. But it hasn't. So the router is basically saying, oh yeah, I can see a valid next hop, and then when the scanner process runs, says, but hang on, this is BGP, that's not valid, we can't do this, so then we also end up oscillating back and forth between the two. If we switch on a bit of debugging for BGP, you can actually see this process going on. Right, and the next time the scanner runs, you see, again, 142.108 has been deleted from that way, it's now being sent where 142.108.10.2. You see this oscillation happening in the scan process. And every time I come across somebody who's got this problem, it's again, do the same thing, and look, you can spot it if you run the particular debug commands on BGP. Okay? And that way you can spot it. You can see prefix being added, taken away, continuously. Okay, so a summary of that. iBGP preserves the next hop information from eBGP to avoid these problems. Next hop self, or make sure you advertise the next hop prefix in IGP. Okay. Most of the problems are because people forget to put the demarcation point-to-point link into their IGP. Okay, that's the most often problem I've come across. The last one I worked on was exactly that. Right? It was a fairly big network, but they were only getting about 3/4 of the routing table set up, and they were like, it must be a bug, it's taking ages and ages, and it only ever gets to 60,000 prefixes, and every time I look at it, it's only about between 40 and 60, and we don't know what's going wrong. And it was simply because the next hop was not in the IGP. Okay, so this is an important one to remember. Inconsistent route selection. There can be problems here too. Right? You've got the different path out of your network. All the time. You reset a peering session, the best path is on another way. It looks as though the BGP best path algorithm isn't behaving or has a bug in it. When in fact it's more due to, I suppose, weaknesses in the decision algorithm, okay? RFC 1771, it says there it's got oversights on it, but I suppose it's a kind of chicken and egg problem. How are we to know that there were potential oversights without deployment experience and so forth? So, the route selection algorithm has left bits that are open to interpretation, with the result being that every vendor has implemented BGP has done the path selection slightly different. Okay? So, basic thing is, RFC says that the MED is not always compared. Okay? Or the way the MED is compared is unusual. As a result, the ordering of the paths can affect the decision process. Right? It depends what order the paths appear in the router, what order they were received. By default, the prefixes are compared in order of arrival, most recent to the oldest. This is where the deterministic MED comes in. If you enable deterministic MED on the router, the paths are ordered consistently, the best path is recalculated as soon as the command is entered, and you really need to enable this in all your routers in the network to try and avoid the problem I'm going to show you in the next few slides. Okay, the diagram is this. We're going to look at router A and to get to AS10. AS10 is announcing this network. Router A will hear it via 2 paths from AS3 and 1 path from AS1. Okay? MEDs from AS3 will not be compared with MEDs from AS1. That's the default action. We only compare MEDs from the same AS. Now, if we look in router A, show IP BGP for network 10, we see 3 paths, 310. This is from, this next hop. This is from that. This is our initial state that we're going to start with. Right? Path 1 will beat path 2 because this one has a lower MED. Right? Remember, you only compare MED for paths from the same AS. So this has got a lower MED, so this one's best path here. But path 3 beats path 1 because it's got a lower router ID. 1.1.1.1 is lower than 2.2.2.2. Okay, so this is the best path in this case. We now reset the peering with 1.1.1.1, and then we find we've got a different best path. Well, when you reset the peering, you're basically bringing this peering session down. So if we go back a slide, hope I'm getting this right. You reset this one, the best path is going to become that because it's got lower metric. So this will be the intermediate best path. And when you reset the peering, so this will be the best path. When you bring things back up, this peering comes up. It's the first one that appears in the list. So path 1, the new path is compared with the current best path. Okay? So path 1 is this one, is compared with that one. Well, this one wins because it's actually got a lower router ID. Is that right? Should be right. Yes, because MEDs aren't compared, so it's a lower router ID. But path 3 beats path 1 because it's an external path, whereas that's an internal. So that's why this one is the best path. Okay? So you end up sitting there scratching your head. You've started off with one path, you've reset the session, it's gone a second way, you reset this, and then the session comes back up, and you end up going this way. Right? And it's like, well, each one was perfectly valid path. It's because the best path selection is vague, let us say. Okay? This is where deterministic MED comes in. The paths are not ordered first by neighboring AS. The best path for each neighbor AS group is selected. The overall best path results are from comparing the winners in each group. Right? So now the best path will be consistent because they've been placed in deterministic order. We've said this is always going to happen. This will always happen. So no matter what you reset, how you reset it, how often you reset it, you'll always get this particular order of paths. The result is with deterministic MED set, you will always get this result. Okay? And this path will always be the best path. Path 1 is best for AS1. Okay? That's the best path for AS1. For these two, well, path 2 will beat path 3 because this has got a lower MED. Okay, this one beats that one because the MED here is lower. And path 1 will beat path 2 because it's got a lower router ID. So this one will always be the best path. Yes, I know this is a different result from the previous ones I've shown you, but at least now we've got deterministic result. No matter what we reset, when we reset it, we'll always get this result for the best path. Okay, and it gives much better stability. Okay, so when to use it? Well, to be honest, I'll just say use it all the time. I mean, I just make it part of the external BGP configuration template. You may as well. Okay. Routing loop. Well, this is an interesting one for confederations. It's more like trying to track the problem down than anything. Traffic will loop between router 3, router 4, and router 2. So basically you find that traffic's going round and round and round within here. We're trying to do a trace to router 1. Network 10 is being originated there. And it just ends up going round and round and round in circles. What's going on? Well, to do a show IP route from each of the 3 routers, well, router 3 is forwarding traffic to 1.1.1.1. That looks fine. Okay. Show IP route 10.1.1. Send it to 1.1.1. So that's okay. Router 4 is also forwarding to 1.1.1. That looks okay too. But router 2 is forwarding to router 3. So what's happening here? Why is it doing this? Show IP route 10.1.1 goes to router 3. But remember, router 3 is there. So router 2 was doing the right thing. Router 4 was doing the right thing. Obviously, that must have been the best way. But router 3 was sending towards router 4. So router 2 was sending towards router 3. Why was this? Why was this happening? Okay. It's very odd that the next hop points to the middle of the network rather than to the network edge. So we look at the BGP path on router 2, do a show IP BGP for network 10. So we find, well, from router 3, we're going to hear, well, this one, that's one path. Another path is this one. And we see that the one from router 3 is the best path. And we're like, why? How can this be? Okay. Well, it's the cost of IGP, but how come it's advertised the next hop of 3.3.3 rather than the expected next hop of 1.1.1? Remember, in a confederation, the IGP next hop is preserved. How come it's being sent with 3.3.3? So we go to router 3 and try and work out what is advertising. Do a show IP BGP network 10. Well, we're doing this. We've got the next hops right, but multipath is being configured. Right? Somebody's configured BGP multipath here to load balance. Okay? Because multipath will reset the next hop back to this. So this is more just an exercise in debugging, trying to figure out where the problem is and working back through the network to spot where it is. Okay? And the whole problem here was because multipath was enabled. You look in the configuration, and sure enough, you see the multipath configuration there. Okay? A maximum pass tells the router to reset next hop to himself, forces traffic to come to him so he can load balance. He was trying to load balance there, and that's what he was doing. Okay? Right. So, I don't think I need to say anything else about that. Troubleshooting tips. High CPU and routed BGP is normally a sign of a convergence problem. So you need to try and find prefixes that are changing frequently. Try and find out why you have got this issue. Have a look at that prefix, track it through your network, try and find out what's wrong. More often than not, it's because a next hop is unstable or a next hop isn't in the IGP. Right? That's really the 2 areas where most of the problems will occur. Routing loop, check the IGP. Loops normally caused by, well, not following physical topology in a route reflector environment. That's quite a common problem. Multipath run within confederations can be an issue. And lacking a full IBGP mesh. You may have accidentally just forgotten to set up one part of your full mesh. It's really easy to do. 50 routers, or how many, 49 routers to go and configure with 49 IBGP sessions. It's easy to miss one. Okay, and you end up with loops like that. So you can do things like have a look at what the routing table looks like, have a look at what the BGP table looks like, try and find out how to get to the next hop. Is the next hop reachable, and how? And you can loads of other things. I mean, I know this is all implementation specific, but use a lot of these commands to try and find out what's going on. You can find out what you've advertised to your neighbors. You can find out what you've got from your neighbors if you've got soft reconfiguration. You can find out what you've received from your neighbors before you've applied any policy. Right? All that stuff is really, really useful to help your debugging problems. Again, clear BGP in. You can get your neighbor to resend updates to you. You can resend your updates to your neighbor. Debugging, I tend to shy away from debugging. I mean, trying to do a debug BGP on a full routing table is fairly scary action. So if you're going to do that, always use an exits list. And always filter the debug. Otherwise you'll get, well, a very, very busy screen. Okay? And you can debug BGP update, but those are quite useful if you want to do it on a per neighbor basis. Okay? What else? So summary, try and isolate problems, use ACLs. Yeah, the log neighbor change, as I said before, is really useful. Check all the reachability things. Now, where are we? 4:30, half an hour to do multi-homing in communities. Okay, might be able to do it. Multi-homing, well, I'm sure most of you know what multi-homing is, but just in case. Multi-homing is when you've got more than one link external to the local network. Right? So you've got two or more links to the same ISP, that's multi-homing. Or you've got two more links to different ISPs or different ASs, that's multi-homing as well. They're usually two external-facing routers. People have multi-homed with only one external-facing router. But that only gives you link and provider redundancy. You usually want to multi-home to give you all three. You want to have router redundancy as well. Okay? You need an AS number. You need an AS number with BGP. If you want to multi-home, you obviously will need an AS number. You get that from the upstream ISP or from your regional registry. Okay. Now, this is advice really to try and start off with. I've seen a lot of people ask questions, oh, I'm trying to do this and I want to multi-home on such and such and such and such. You can do a lot of things with prefix filtering, AS path filtering, and with route maps. You can do filtering based on that as well. And I'm always encouraging people, try and keep things simple. Start off with a simple configuration, right? I think part of the problem with newcomers is asking questions on mailing lists. How do I do this? You get the experts replying with their nicely tuned bit of configuration that's worked for them for years, which will work very, very nicely for them, but it's probably a bit too complicated for the newcomers, right? So the basic principles I've got here, when I do a whole one-day multi-homing tutorial, so trying to do one in 30 minutes is a bit short. But in that one-day tutorial, I encourage people to use prefix lists, filtering prefixes, filter lists to filter AS numbers, and route maps to apply policy. Okay, as I was saying, again, when trying to configure policy, it pays to keep it simple when you start off. So in these examples here, and I've only got a couple of examples in these slides. There's just not enough time to try and give you the full works. But use prefix lists to filter prefixes, use filter lists to filter on ASs, use route maps to apply policy. If you follow those three principles, keep it clear in your mind how you're going to do it, it becomes really straightforward. Okay, and it avoids confusion. There's nothing worse than trying to dig through a route map that's filtering some prefixes and applying policies in other places and trying to work out what it all does. Okay, keep clear demarcation lines on the different things. Now, some more basic assumptions. Must announce assigned address block to the internet. I say must. I think if you look at the registries, T's and C's, they say things like, you should announce your aggregate to the internet. It's certainly true for APNIC. But the thing is, if you don't announce your aggregate to the internet, you will end up with reachability problems for your network. So it's always good practice to must. Always announce your aggregate. Always, always, always do it. Okay, so in these examples I'm going to give you, I'm always announcing aggregate. You can also announce sub-prefixes, but reachability is not guaranteed. Okay? Right, the regional registry minimum allocation is a /20. All three registries do this. Several ISPs filter the regional registry blocks on this boundary. So if you announce a 21 out of that address space, it will not be accepted by several ISPs. Now some ISPs, well, some people call these people net police. Okay, I put it in quotes because do that. But actually, this is a filter list, a prefix filter list I picked up off a mailing list not very long ago. And yeah, they take APNIC address space and they apply an ARIN and RIPE NCC and they apply basically a prefix range filter like that. They allow all prefix sizes from /9s to 20s in each of the registry blocks. Okay? And so if you announce anything bigger than that or smaller than that, it will not get into these people's networks. Now, you may say, oh, well, that's their big problem, but then again, the other people, the people who are doing this filtering will say, well, people can't announce their things properly, then that's their big problem. Right? If some of these are content providers for your popular websites, your customers are going to start complaining because they've got no access to some of the popular websites. What are you going to do then? Who do you blame? Do you blame them or do you blame you? I will stay out of the politics, but it's just to be aware that there are a lot of ISPs who are doing this. They don't want to carry 105,000 prefixes. They can apply these filters and reduce it to 70 or 80,000, or even less.
85.
85.
How about then that leaves lots, customers have small blocks.
Mhm.
There's last 24.
Yeah.
Doesn't that really lots of work you don't have for the customers who want to have them, ISP revenue?
Yes. Right, it's meant to punish ISPs who won't and don't aggregate, but it impacts legitimate multi-homing big time. Okay? And especially from my part of the world, it causes big problems in Asia-Pac. Big problems. Where domestic backbone is virtually unavailable, or you can't get it, so ISPs are going to take their /19 or /20 they get from APNIC and chop it up into little pieces to try and get any multi-homing working at all. For example, if you look in India, well, the 8 exit points, the 8 big cities in India, each one has like an OC3 or so to the US, but you may have a 2 megabit circuit connecting the cities together. So of course all the traffic is going to go out each of these international OC3 links. And some of the guys there trying to do multi-homing really have a hard time with a lot of the net police type filtering. Right? They get a lot of suboptimal routing. Okay, so it causes problems there as well. It's also hard to maintain. Witness the discussion on the mailing list recently about Network 80 and 81, which was given to the RIPE-NCC about a month ago. You've got to know that the registry has got a new block and they're going to start allocating from this new block. Okay, you've got to watch the mailing lists. So you've really got to be on the ball if you want to try and do it. Be aware of the impact, what it's going to do. If you're going to try and do something like this, you have to try and keep it current. There's no point just setting it up and forgetting it later. Okay. I mean, my own opinion is there's got to be better ways of trying to do this than just putting these filters on. But that is my own opinion. Okay. So, multi-homing. First situation we could look at, stub network. You've got a situation like this. Customer, maybe he's got a couple of links to you, but here they just connect the 2 parallel circuits between 2 routers. There's no need for any BGP here, no need for an AS number, nothing like that. You just point static default to the upstream on the 2 circuits, and that's all the load sharing you can hope to get. Okay, that's all you can do BGP on this if you want to, but I think it's a fairly big hammer to crack this particular nut. Okay? Where you will use BGP is a more useful situation like this, where you connect to your upstream ISP in 2 different points of presence. This is quite popular type of multi-homing. You don't actually multi-home between 2 different ISPs. You just buy multiple connections to your upstream and connect to different points of presence in the network. Use BGP for this. Some people try and use OSPF or RSIS or other things to try and do this load sharing. Again, you run the dangers with an IGP of running an IGP into your customer network. Your customer may be running OSPF as well. Well, don't you want all your customer OSPF prefixes in your backbone and vice versa? I've seen that happen quite a lot. Okay, so don't run an IGP here. Also, use a private AS number. There are 1,023 of them, so it's very easy to do this. Okay, use a private AS, they multi-home onto your backbone. It's all done by BGP, and it's a nice, easy configuration.
This is not using confederation already.
This is not using confederations, no. I've got an example of how this is done coming up. If you're a true multi-home network like that onto the different ISPs, well, then this is a different situation altogether. Okay, there's so many configuration possibilities here. What about multiple sessions to one ISP? Well, if you have a situation like this where you've got multiple circuits, you can use eBGP multi-hop. where you run eBGP between the loopback interfaces. So you can load share over these three circuits. If just pointing static default at both ends isn't enough for you, or the traffic is too strange to try and deal with that, you can use eBGP multi-hop. Or you may be connected to other service providers as well. And this is just one connection that you're trying to load share the circuits over. Right, so you run the eBGP to the loopback addresses. eBGP prefixes are learned with the loopback as the next hop, and then just set up a static route pointing to each of the serial interfaces. And that works really well. Watch this number here. I've seen situations where all these links have failed, and the eBGP multi-hop's gone around some other way. I'm really surprised the ISP are concerned. You've got to be careful using eBGP multi-hop. Don't set more hops, TCP hops, than are really necessary. Okay? Oh, this one, you could use BGP multipath. Multipath basically means the router will install parallel paths in the forwarding table. Okay? In this example is a limit of 6 parallel paths. We've set maximum paths 3, so the router will do load sharing over these 3 paths. The downside is you need 3 separate eBGP sessions with your neighbor. If you're carrying the full routing table, this could get expensive. Okay? So this one, probably more use for you going to a customer rather than you going to an upstream where you're getting the full table from. Okay? So that's the other option. The common one that I see between ISPs and the customers and so forth is something like this: separate routers, trying to use defaults, and then learn and advertise prefixes as necessary for better control. Okay? You need some planning. You need to have some work there to try and achieve a load sharing. There's no magic solution. If I had $1 for every ISP who asked me for the magic command that will set up all the load sharing for them, I'd be quite well off by now. Okay? But unfortunately, there's no magic solution. You need to sit down and understand what you're trying to do to set this up. Using private ASs, well, an ISP with lots of single home customers, as per RFC 2270, that's a good application for private ASs. Obviously, confederations we've seen before, and corporate network with several regions and connections to the internet only in the core. Often, certainly multinational corporates like splitting their networks up into different regions of control, but may have HQ that controls internet access. So they have different autonomous systems around the globe, but only HQ has the real one that connects to the internet. Okay, so that's a kind of delegated authority. So those are the main reasons for using a private AS. But they are used a lot. Okay? As I said before, removing the private AS. This command should be a standard part of eBGP configuration everywhere. Okay? Make sure that it's all part of your eBGP configuration. You don't want to leak private ASs out into the routing table. I don't think it causes any damage, but it's just they're there and they shouldn't be. There are various rules that go with them. I won't go through them, but you'll get them on the slides from the NANOG site if you want to look later. Now, I've just got about 2 or 3 examples in here just to give you an idea, because I don't have enough time to go through everything. Here's an example: 2 links to the same ISP, give you some redundancy and some load sharing. So simple picture, AS109 I use in these examples is Cisco's AS. So 65534 is the private AS. We've got this link between router A and router C. We've got a link between B and D. What we want to do is try and load share over these 2 links, but provide redundancy. So if this link breaks, we get backup over that one. Router E is the one that removes the private AS and any other customer sub-prefixes that may be announced to the internet. Okay, so what we do? Well, we announce the /19 aggregate on each link. Always, always, always announce the aggregate. That's really important. We then split the 19 and announce it as 2 20s, 1 on each link. There's no harm in doing that. Okay? It gives you basic inbound load sharing. Okay? I mean, if you're assuming traffic is all equal and the host utilization of your address space is all equal, then this is a nice first cut. Don't try and cook up the most complicated configuration to do your load sharing. Start with something nice and simple. See how you go with it. If it doesn't work quite well, then change things slightly. Vary the split. You may want to split it into a 20 and two 21s, and so forth. Okay? Gives you basic, accept the default from the upstream. That will give you basic outbound load sharing by nearest exit. That works fine in most cases. And this is okay as a first approximation. Right? Last time I talked about this, somebody from a hosting site jumped up and said, "Ooh, well, this doesn't work for hosting service providers, where the bulk of their traffic is outgoing." And that's where we've got to deal with the situation in about 10 slides' time. Okay, I've included a router configuration. I'll find that's quite useful to explain the concept. So we've got the /19, that's our aggregate, with the static route there, making sure the aggregate appears. We've got our /20 that we've split it into. The remote AS, prefixless router cout, we're only accepting the default from our upstream. So we're announcing the 20, we're announcing the 19 to their upstream. Okay, that's quite easy. Router B configuration, remember that was also an AS65534, same thing, but with the other /20. Router C. Well, this is the ISP. ISPs like to keep things simple for themselves. They don't like custom configuring every single customer they have. They want to use the same configuration. So this is fairly standard. Remote AS65534, default originate, we're only going to send the default route to our customer. Prefix list, customer in, so we're going to accept the 19 and the 20s. In fact, you can change this. If you're going to give your customer enough rope to change what prefix he announces, like you could announce a 21 or a 22 or a 23, well, just put it in there, 19 LE24. Then he doesn't have to phone you up and say, I want to tweak my load sharing. Right? Just allow him to announce any sub-prefixes from his /19 towards you. It doesn't matter. It's not going to have internet visibility anyway. It's only within your backbone. Right? So you just allow everything in from your customer, pretty much from his block, only allow the default out. Router D configuration is exactly the same as this. Okay, it's exactly the same, only the neighbor addresses are different. Okay, so the load sharing configuration is only in the customer router. Well, I don't know about you, but certainly when I was working in ISP, the amount of customers we had who wanted to tweak and play with their own BGP configuration. And it was like, oh, well, we don't really want to do this. And some people would just let them do it. And they were so happy, they were just delighted they could tweak BGP and play with it and all the rest. So this one, in this example, I put the configuration on the customer router rather than the ISP router. You find a lot of customers, I suppose they fancy themselves a bit as BGP experts, so if they can get to play with something like this, they feel really good about it. And they get to learn a bit about BGP also. Okay? Now, the upstream ISP has to remove customer sub-prefixes from external announcements and remove private AS from external announcements as well. I haven't got a configuration example for that, but you have a simple prefix filter that only allows the customer aggregate out, and you have the remove private AS command that strips out the private AS number. Right, two links to the same ISP. In other words, you've got multiple dual-homed customers. For this example, RFC 2270 is what that's been written up in. I don't know how many people do this, but I think it's quite neat. The funny thing is, when I ask people why they don't do it, they say, oh, you can't do this because BGP loop detection will cause this all to break. And it doesn't, not a bit. You'll see why in a minute. You've got multiple dual-home customers, you can use the same AS number. Right? Some ISPs use private ASs. I know some who use public ASs as well. They may have got a spare public AS, so they use that for all the dual-home customers. Okay? Right, so moving on to the next bit. Customer announcements, well, that's the same as the previous example. We can use the same private AS. If you don't believe me, it's all written up in RFC 2270. Address space is not overlapping. The reason it works is the customer only hears the default route. Right? The customer only hears the default from the upstream. The upstream does not send the full routing table to the customer. There's no need for it. Okay? So you don't have a problem of split up ASs or routing loops. AS path loop detection. Router A configuration, B configuration is the same as the routers previously. You get economy of scale here. You can set up a template for all your BGP customers, there's pretty much this, and just give it out to them. Do this, do this, do this, and it's the same for every single one. You've got the /19, the /20, prefix list out, going to send these two networks out, only going to accept the default in, and then the two static pull-up routes to make sure the BGP prefixes are announced. Router D1 configuration is similar, but for other /20. Right? All your customers will have this configuration. The addresses will be different, but otherwise the configuration will be all the same. This is where the economy of scale comes in. Right? Router C configuration. This is your aggregation router. You set up a peer group for these customers. Neighbor BGP customers, you call the peer group BGP customers, just to be nice and clear about it. Remote AS you can put in, default originate you can put in, prefix list default out. You're only going to send the default route to your customer. And then neighbor peer group BGP customers, description customer 1, prefix list. Remember, inbound policy is different. It can be different for peer groups. Only outbound policy is the same for peer groups. Okay, and then for all the customers you have, you just go bang, 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 in like that. Okay, next slide, there's customer 3, and any other customers you have. It's very, very easy to add another BGP customer to this. And then you just create an individual prefix list for your customers, and you're done. Router D configuration is virtually the same. And router E, well, let's assume the customer address space is not part of that upstream's block. Then router E will have remote AS to his upstream, remove private AS to strip out the 65534. Prefix list, customers out. We just let the customer /19 networks out. Okay, becomes quite a simple configuration. The private AS is fully visible inside AS109, but for the rest of the internet, it just looks as though this ISP AS109 has got lots and lots of customers, statically connected customers with the /19 block. If customer prefixes come from the ISP's address block, don't announce them to the internet. Announce the ISP aggregate. So say the ISP aggregate, well, it's a /13, which covers all these previous examples. Then all you need to do is prefix list my aggregate out. You don't even need to strip the private ASs, because they'll be removed anyway by this prefix list, because this prefix list is only letting the /13 out. Okay? That's quite easy to do. I really like RFC 2270, and it's much better trying to get your customers to multi-home onto your own backbone rather than between you and another ISP. Okay? I mean, talking from the ISP point of view, as soon as you multi-home to somebody else, then there's a potential of, you might lose them as a customer because they might like the other ISP better, and then multi-home onto somebody else, and so forth. So if you can sell this as a service to your customer, multi-homing onto different points of presence, it's actually really simple to configure it. Now, that's links to different ISPs. In this case, we'll want to try and announce 19 aggregate, as we did with the two links to the same ISP. Split the 19 and announce it as 220s. So we're still announcing aggregate, but we're also announcing the two sub-prefixes. It gives you basic inbound load sharing. I mean, this may not be enough to start with. Well, it'll be enough to start with, but it may not be enough as your network grows. Right? But it gives you a start. Don't try and come up with some convoluted load sharing for the very first step. Start simple, make it more complicated. And again, when one link fails, the announcement of the 19 aggregate via the other ISP ensures continued connectivity. Always announce the 19, always announce the aggregate. Okay, so that's the pretty picture of it. So router A will announce 20 and the 19 block. B announces the second 20 and the 19 block. Again, I've given you a bit of configuration. We've got the 19, we've got the 20. Prefix list, first block out. The first block is given in here. Default. Again, we'll only accept the default from the upstreams. Default's a good first approximation to start any load sharing. It's usually more what most people need. Okay, router B looks similar. It's just for the second /20, so it's very, very similar. Moving on. Okay, two links to different ISPs, so slightly more controlled load sharing, just to give you some other ideas of what can be done. Again, we announce the 19 aggregate on each link. We always, always, always announce the 19 aggregate. First link, we announce the 19 as normal. Okay, we just announce the 19. On the second link, we announce the 19 with a longer AS path, and announce a single /20 subprefix. Okay? This gives a little bit more control of load sharing. Right? The /20 will go to your upstream. It may go further than your upstream. You don't know. I mean, maybe you can talk to your upstream and find out what he's announcing to the internet. He may send everything. There may be somebody higher up who's filtering. But this way, with selected leaking of subprefixes, you can improve your load sharing also. It's much better doing something like this rather than taking your 19, splitting it into 32 /24s and just spraying them out and seeing what might happen. But you'll be surprised how many ISPs just take the 19, chop it into these 24s, and announce 32 Class Cs. That's the language they use. Okay, Class Cs were history in '94. But people still talk of announcing Class Cs to the internet. Okay, so take it small. Take something like this, announce a single 20, see where you get. And then varies the subprefix size or even the AS path length. Okay, it depends on your upstream's connectivity to the rest of the internet. So the pretty picture, we announce the 19 this way, we announce the 20 subprefix and the 19 with a longer AS path. Okay, we don't even have to announce it with a longer AS path, it's just showing you a possible example. Right, all traffic for the 20 subprefix from the internet in 108 will come in this way. Traffic for the other /20 will come in around that way. And it depends where the filtering is or what's happening with the AS path will determine which way traffic will go. You know?
Take care of load sharing in both the directions?
No, this will only take care of load sharing. It's your announcements going out, so it's traffic coming in.
Not outgoing.
Not outgoing traffic, which are the next few slides. Okay. Okay, so configuration. Well, example, again, we'll only accept the default from the upstream, and we'll only send aggregate out. That's easy for router A. Router B, we're doing something a bit more complicated. Again, we'll only accept the default in. So the outbound traffic flow is going to be nearest exit, which might be enough, might not be enough. Prefix list sub blocks out, so that's what we're going to allow out. It's going to be a 19 and 1/20. And we'll run route map router D out, which is where we're going to apply the policy. And the route map basically says, well, if we're going to match this aggregate, which is here, the /19, we do an AS path prepend of 2 ASs. Everything else we just leave alone. That's a simple example of trying to do it. As I say, there are so many possibilities here, so please don't ask the what if, what if, what if. I've got a whole presentation that covers a lot of the what if scenarios, just to give you an idea. The main point is keep it simple. I think it was Paul Ferguson who always said, KISS, keep it simple, stupid. Right? Keep it simple. Right, so that was inbound traffic. What about outbound traffic? Well, situation, we've got one upstream, one local peer. I'm going to overrun by a few minutes, but I've only got about 30 slides left, so I will go quickly. One upstream, one local peer. Again, announce an aggregate, 19 aggregate on each link. Accept the default route only from the upstream. Try and get away from the thing of have to have the full routing table from the upstream. Okay, accept the default or a network which can be used as a default. Okay, so the picture could be something like this. The configuration, blah, 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 blah. But again, from your upstream, only accept the default. That's all you need. Because your upstream's got the full routing table, knows how to get to the rest of the internet. Your local peer has local routes, so you take all the local routes from him. And that's a fine first approximation. But again, you'd be surprised how many people in this situation will take the full routing table from upstream and local routes from the local peer. They don't need it. Okay? I'll jump over that one. Okay, 2 upstreams, 1 local peer. Well, the 2 possibilities, accept the full routing from both upstreams, or accept the default from one upstream and some routes from another upstream. As I said, most people seem to go for this. I'm not quite sure why. And I mean, maybe there's some perception to have all the specific paths in the routing table is better than just accepting a default. But you've got to work so hard, and you've got to buy such big equipment just to deal with this. Okay? Another thing is you're carrying full routes in your backbone. I mean, why do you want to put up with the possible instability and so forth? And the Tier 1 ISPs will need to do this, but there's probably a lot of question as to why anybody else further down the the chain needs to do it. Okay? So that's the picture. Router C, who was router C? That's the one upstream. Okay, so router C to one upstream. Well, we're going to take the full routing table from them. So we've got the RFC 1918 access list. CL in the tutorial for that. And then you can do some kind of filtering. So you accept his prefixes, any prepends that he may do, and then you accept his neighboring ASs as well. This is just an example. So that's the sort of thing you can do. So you're sending the full routing table and you're chopping a fair chunk out of it. Right, so from these you're chopping from these you're actually setting a high local preference. Everything else you're setting low local preference. Right, this is still taking the full routing table, but setting some of them to high local preference. So for these paths, you'll go this way through router C, and for every other path, you go out through router D. Okay, so that's basically what I said. Router D configuration is the same as router C without the route map. It hears the full routing table. Right, so the link through router C breaks, then you got back up through router D. D breaks, you get the back up through router C. Okay, so that's how to do it with the full routing table. It works fine, there's nothing wrong with doing it this way. But it's expensive, you need lots of memory, and it's going up and up and up. The routing table paused between January and probably end of March, beginning of April, but it started its sprint on upwards in the exponential growth. I mean, it was 103,000 prefixes a month ago, and it's now 106. It was 106 this morning. Okay, and it was only 105,000 a few days ago. So it's rattling on upwards again. Oh, sure. Yeah, the size depends on where you look. I mean, some people I know are sitting with 75,000 prefixes. Others I know are sitting with, the full view is about 118,000 prefixes. So it depends where you are. My view is 106. So, contributes to network instability. You're carrying all these prefixes. If something changes, then your IBGP, your router's got to deal with it and takes time and all the rest. You don't really want this in a smaller network. You need to play the preference games. Okay? And again, this example it's only an example. And again, for real life, you'll need fine-tuning for it. So don't just cut and paste this and use it and say Philip said so. Right? You will need to fine-tune it. If you use partial routes, then it gets a lot easier, I think. RFC 1918, again, you block the default, you allow the default through. Prefix list my block out, so again, you only send this aggregate out, and then filter list 10 in. You're now filtering what the upstream sends to you. And filter list 10 could be something like that. And you're actually blocking prefixes coming from upstream, so he only sends you these. He may still send you the full routing table, but you only block everything apart from these prefixes. Okay? And then once you've settled with this, you're happy with it, you can maybe talk to your upstream and say, okay, you're sending me the full table, but I'm only accepting these. Can you put this on your outbound filter so we don't have to send the full table to me all the time? Some of them may be open to that, others may tell you to take a hike. Okay? But notice what I'm doing here. I'm accepting the default route, and I'm marking the default with a low local preference. Okay? Setting in a low local preference. This is the backup default. And router D configuration, I'm only accepting default from upstream. That's all I'm accepting. And you get exactly the same load sharing with this as you did with the full routing table example. When I gave this configuration to a Filipino ISP about 3 weeks ago, they were carrying full routing table from the two upstreams. They changed over to this, and he's now delighted. He's noticed the huge stability he's got in his network, which he just didn't have before. Because he was trying to carry full routing table over fairly unstable upstream links to the US. It was no fault of him, it was just the nature of the connection. And now he's got this, suddenly everything works. All because he just threw away 106,000 prefixes. He's now got something like 3,000 prefixes in his backbone rather than, 230,000 paths that he had. Okay, so what we're doing, C, we take the full routes from 107, get them to send less, and then we filter everything so only accept 107 and 107's neighbors. Okay? Etc. Okay, partial routes, not expensive, network's more stable. Again, just an example. Right, using communities. I'll be quick with this, I promise. Right, the 2 bits, RFC 1998, that's Tony Bates and Chen RFC and what they did at MCI. And then I've just documented some examples of service provider use of communities in their multi-homing or BGP customer situations. Right, RFC 1998 describes how to implement load sharing and backup on multiple inter-AS links. The idea behind this is to give control to the customer and to simplify the upstream configuration. Again, when this RFC came out, we deployed this in the UK network, and it made life much, much, much easier. You can give the control to the customer, tell the customer, do this, do this, do this, and they could do things how they wished. These 4 communities had a particular meaning. Your AS number, :100, if your customer sent you this, it became the preferred path. If your customer sent you your AS :90, it was backup route if they were a dual home customer. 80, this was main link was to another ISP with the same AS path length, and 70 was main link to another ISP. So those were the 4 definitions. The customer router configuration, well again, you can just set up a template. You give your customer this, you explain to him what it does, and then he's quite happy playing with BGP and communities. So he moves from being a beginner in BGP to feeling as though he's a real expert in BGP because he's now using communities. Right? And you can basically get a customer to send the community just based on what he wants. The ISP router configuration, well, you just define all your communities there, and then in the route map, well, if it matches this one, you set local preference 70, and so on. You can just set up a simple BGP customer route map that sets a local preference appropriately. Okay, so just to show you a quick example, this is similar to one before, but A to C is the primary path, that's the backup path. Again, we make this /19 aggregate in each link announcement. The router A was the primary path, so we just announce the aggregate, we accept the default in. Router B is the backup path, so we scan that send community, we send the aggregate out, default in, but we then have a route map. Router D out and router D in. So router D out, we send a community 109.90, and that signifies to the upstream that that is the backup path. So rather than sending an MED, which we had a discussion at the start, a lot of ISPs not accepting any MED anymore, that's because they generally try and accept or use a community-based thing. You send him this community, he will then tag local preference of 90 on what he hears from you. Okay, so you send him this community, he will tag that path local preference 90. Of course, you will need to set local preference 90 so that this is the backup path as well for inbound. Okay, for inbound announcements. Okay, and that basically does it. And if you want to swap things around, you could put this sort of configuration on router A as well, but just send the opposite way around. So you give the control to the customer. And the router C configuration, well, it becomes beautifully simple. Default originate, prefix list customer in. Okay, that was the same as before. Router D, which has the backup link. Okay, you just have a route map, BGP customer in, and that takes care of setting local preferences, the policies, as per 1998. And you just have match community 90, set local preference 90 is the particular one we're interested in. Okay, and that works very, very well. That way you give control to the customer. So if the customer wants to swap which is the primary path, which is the backup path, you then just tell them, oh, well, send this community. And it's like, oh, yeah, wow, great, and you can do that. Okay, and you don't have to be involved. They don't phone you up. They don't have to wait in your support line, phone queue, take up valuable time and resources. You don't have to do a custom configuration per customer. It's all template-based like this.
Have you found that most ISPs you work with have implemented this compliant with 1998?
Question is, have I found that most ISPs I work with have implemented this? No. Very few. Very, very few. Very few actually have implemented anything like this. I mean, a lot of them have implemented communities, but just for their own particular uses. I mean, in my time at UNet, I implemented this because it was just trying to manage all the different customer requirements. We had other communities as well because they want to do lots of weird stuff. But with other communities, we just gave it all to the customers. Customer, just do it. You know, it's like, don't bother us. You know, our network's set up to deal with everything you send us. So we could have with a long list. I think it's still there. If you look in AS1849 AS object and in the whois, right whois database, you can still find what the policies were. I think it may have disappeared now, but
No, 702.
yes, I know it's now 702, but the AS object is still there. I think if it hasn't just disappeared. Okay. Right. So here's some working examples. So RFC 1998 is okay for simple multi-home customers, but I find that ISPs have created a lot of other communities to handle more complex situations. So these are some of the things I've picked up. Some of these from my day, some of them, well, some of you will recognize. But this is typically what people are doing. Right, apart from 1998, they've set up this one. This is the opposite to the 80. I've seen that quite a bit. 122 and 121, these are quite interesting ones. It's telling you upstream to set local preference unannounced to their upstream. So I've got pictures for some of these. 81 and 82 I've seen a bit. You set local preference low and high on an upstream and low on an upstream. So it starts getting a little bit harder to think about. This one, announce to customers with no export. If your upstream supports communities, you can do that. Or this one, AS20, announce only to backbone and to customers. I've seen that one used. These three quite common as well. If you send this community upstream, it tells you upstream to announce your network with a 3 times AS path prepend, or a 2 times prepend, or 1 times prepend, whatever. Okay? And I find these ones, or variations on this theme, are the most common used ones. I mean, no doubt some of you who are using communities will have other things as well, but yeah, there's a lot more. Maybe somebody could write a new RFC about what people are doing, because I think it would be quite useful. I get asked so often, well, what are other ISPs doing? Maybe I should write one. But, these are certainly the very common ones. So examples. This one's a bit strange. 109:122. If 107 sends this to 109, it means that, well, he sets a high local preference here, but he also sends a high local preference to AS110. So traffic from 110, 109 to 107 all goes through that link. Okay, seen that one. This one's a bit bizarre. High local preference there, but he makes it low going up to 110, so the preferred path goes around that way. You may want to do this. 109:3, prepend any announcements to peers of 109 with that. So AS109 is very definitely my backup transit AS. 109:20, don't announce outside upstream's customer base. Okay, and 109:21 is very similar. And that is it. That is all I have. So we've covered those 6 topics in record time as well. I hope it wasn't too fast for all of you. These slides will go up on the NANOG webpage. As I said before, I didn't have time. I only finished this presentation a couple of days ago, so didn't have time to put it up on the webpage. We'll also put it up on, our group who work with ISPs have got a private webpage on Cisco's website. It's www.cisco.com/public/cons for consulting, CONS. It's not searchable from CCO at all. It's a secret webpage just for ISPs. We don't want to tell the whole wide world about it. But there's a lot of stuff in there. I'll put this presentation there as well. But a lot of other things, including all the workshop materials, more in the multi-homing presentations I've mentioned. So if you find any of that useful, feel free to download it and pass it on to whoever you wish. So it's www.cisco.com/public/cons, CONS. Okay. So are there any questions, comments, thoughts? If not, thank you very much.